Okay.
Uh,
So while we get settled and reach out to George King, I'll just give a little introductory note. Welcome everybody. The task being undertaken by this committee of the National Academies of Sciences, Engineering, and Medicine is to assess potential causes, consequences, and remediation of plug failures. You can find the full statement of task on the website, which I'll put a link in the chat for that. You can also find by this link the committee bios. There's a kind of table of contents with links to the left of your screen. From this link, you can navigate to meetings, meeting materials, committee member biographies, that kind of information. To give a sense of the format of today's meeting, we'll have
Okay, I got it.
oh,
All
hi
right,
George, welcome
bye.
in.
Okay, great.
Thank you so much. Thank you, Maleva. So we're just getting started here, giving some introductory information. To give you all a sense of the format of today's meeting, we'll have our first panel session with George King and Dwayne Purvis. And that will close at about 11:30 a.m. Eastern time. And from there, we'll have a lunch break and we'll reconvene at 12:30 p.m. Eastern time with our second and final panel session of the day. And I'll introduce those panelists at that time. In addition, I want to note that this is an open on the record session, so we're recording this session. We may address questions from the chat provided by our public attendees, but the priority of this meeting as an information gathering session for the committee is to make sure we address committee members' questions for our experts for the day. And in terms of what it means that we're having an information gathering session, the committee here is in the process of assembling materials that it will examine and discuss over the course of compiling findings, conclusions, and/or recommendations that will be written in their final report at the end of this process. I'd to that point, like everyone to remain mindful that the committee at this time has made no conclusions. This is just the beginning of the process with our first formal information gathering session. And just generally, of course, we ask that all attendees be respectful of each other throughout the meeting. Okay, and with that, Sam, are you ready to share? We'll start with George King's presentation. So we'll go ahead and put that up on the screen and run those slides for you, George.
Okay, thank you.
And if you could briefly introduce yourself as well, George, that would be great.
I'd be glad to. George King, I worked in the oil and gas industry for, I think, 54 years now with both majors and independent well companies. And my main structure here in this area has been well work and finding problems and solutions to wells where we had leaks or underproducing wells, various things. So, with that, they'll bring up the slides. All right, there we go. All right, today, and by the way, thank you very much for inviting me to speak. Quite honored by that. Uh, I'm going to look at some of the pollution risk factors from the orphan wells and also get into areas where you can detect it uh, and what's not a really big problem. But I'll work through this as I go along. All right, next slide, please. All right, just a quick disclosure here. I've worked quite a while through all this. I'm a registered professional engineer, have been for about 48 years, and worked at a variety of companies. And I'm going to say here that the opinion statements and estimations are drawn from experience. I put as much um, accurate information that I can vet as I can in the program, but there'll be some, and I'll label it, that are nothing more than opinions. Okay, next slide. All right, first off, if you look back in time very quickly here, we're going to look at eras of development. And honestly, the oil and gas industry started in the US about 1823. Oil started a little bit later than that, up in the 1830s, 40s. But most of the wells in that area or in that era, very, very shallow and oftentimes highly polluting simply because they just let the methane escape as they produce the oil. And so in red, I've limited this. There's a lot of wells, probably 102,000, maybe 200,000 even, that were drilled in Northeast US over a period of about 70 years that weren't cemented. We didn't use cementing in wells until the early 1900s. And before that, if there's a well there, it was not properly abandoned. We don't have a record of where it was. And basically, you find these things by accident. In 1916, they started using cement. A little bit later in the 20s and 30s came rotary drilling, where they weren't just venting as they were drilling, pressure control, etc. In 52, you started seeing a lot of fractures, which reduced the number of wells that we had to drill. And then we started getting into some things that actually made things better in the well integrity side. And I talk about well integrity because it is a lead in to the problems you may or may not feel as you get into orphan wells or those wells that were shut in for a long period of time. Okay, now there's things that you can read for yourself as you go down through there. We're getting less and less polluting as we go along, but the big factor here is a lot of shut in wells waiting on repurposing, waiting on something or other that really need to have a better seal put in there. So we need the plug and abandonment. Next slide, please. All right. So a lot of wells worldwide, the counts are really estimates. Nobody knows exactly for sure, but you can go by era of development. And as I showed in the last slide, there's a lot of changes have been made. Now, today's abandoned or orphan wells, or even the ones that are just shut in, have a minority of population of the wells that are going to leak. Most wells won't leak if they maintain some good well integrity. That is, if it was built that way. Because these wells, we have records of wells that have been on production for over 100 years that are not leaking. So if it's done right and nature cooperates here, and I'll get into that a little bit later, that these wells have a very good track record up to a point. All right, next slide, please. Now, this is a generalized plug and abandonment. And just very quickly, as we work through here, we're trying to isolate zones, protect zones of fresh water, eliminate zones of corrosive salt water, seal in the hydrocarbon producing areas, and hopefully can prevent mixing in here. The issue is this is still steel casing with couplings. And if you don't have a good cement job in here, which is the bottom line for almost any wells, is getting a good cement job to really provide a seal over all of these areas. All right. Now, The uh, I see one of the slides coming up. I'm going to cover the scrap metal deal in just a minute or two. Go on to the next slide. And by the way, you could probably have a week-long class on all the things that can go wrong and how to correct them or just totally prevent them. We don't have time today. So the comments, and this is my experience, no leak or low leak wells have good pressure type barriers, little or no drilling problems. You start having drilling problems, sidetracks, those types of things, and I'll cover that in a moment or two, you're going to have problems. One of the problems that is still with us today is we're using the non-premium connections in the casing, and those are not gas tight, and their seal will last only as long as the thread compounds will. So this is one thing we've been trying to get companies to move away from is these 8 round or other types of threads that don't have good steel to steel sealing. All right. But the bottom issue here is you've got to have high quality cement over this whole zone. Oftentimes, cement is an afterthought, and it really should be the most important thing coming. Because if you have good cement, that well is going to last for a long, long time. Now, wells with leak problems, here's the surprise. Most of the wells with leak problems we've seen come from the era where you've got an oil field boom going. You've got all kinds of people coming in. I mean, if you have a heartbeat, you can get a job in the oil industry. That was its reputation. But there was some really sloppy work that went on this time. And so you didn't get what you need. Now, if you when you start looking for risk areas, boom time wells and highly times get a red flag. Now, wells with the leak problems also include some inexperienced developers here, maybe some older wells, and any place where the failures weren't investigated. Next slide, please. All right, now let's estimate a risk level here for a shut-in or an orphan well which isn't leaking yet. And over time, I'm not saying that all wells won't leak over time, but most of the ones will go for a long, long time if they're done correctly. So look for well construction quality, the design, the drilling, the cementing. Is it vetted? Is it tested? Is it really designed well? Accuracy of the well files. And this is a problem because a company that drills a well may produce it for a while, sell it to someone else who sells it to someone else who sells it to someone else. And pretty soon, and I've seen this dozens of times, where we pull up the records that we have for how that well was completed, what size casing, what grade of casing, what corrosion resistance it has, and there's nothing in the file because they're gone, and it's very difficult to find information about that. So keep your eyes open for that. Look at if the well is leaking, look at the wells around it. If the wells around it are leaking, you have probably a field-wide problem. If it is just a solo well that's leaking, then that may be an entirely different deal. That may be easier to do and to seal. All right. So look for differences in development or changes in the ownership. Now, how many tested pressure barriers are in the wells? We'll look at pressure barriers in a moment or two, excuse me. But those, if it's a good barrier, it will hold on almost no matter what. So geologic changes, seismic subsidence, corrosive fluids, a karst, a sinkhole developing, those are the red flags that should come up. And more missing info or confirmed problems, that leads to a higher risk. and possibility of this well turning from a non-leaking well into a leaking well. Next slide, please. So let's start orphan plugging success factors. And there you go, right down the list of the condition of the drilled hole. You look in there, you see a lot of deviation, a lot of dog legs, washouts, side tracks, milling. There's a lot of things. You look for that, and those are early indicators of places that may develop leaks. Now, casing, coupling, cementing, talked about a little bit. The quality and placement of cement slurries, I'll keep coming back to that over and over. That is critical. Now, it may indicate success of long-term sealing, and we're talking about the cement. This is a well I'd worry about less than any other well. Now, the type and success of artificial lift and secondary recovery methods, those are factors, but they factor in well down the road. So find out what P&A approaches that have been used and how diligent the company was in moving into shut-in wells when they know they're not going to be able to repurpose this well. And if you have companies like that, that's a plus. If you have companies that just have a huge pile and just shut in wells and just continue to sell those out, that's a red flag for me. And also some of the geoscience things that you'll see from time to time. But really, you identify the wells that are hardest to plug and most likely to leak as one of the ones that I would say put to the front of the line in terms of minimizing the emissions and leaks that you get from an abandoned well or a shut-in well. All right, next slide, please. The risk by type of well. And then over here on the right-hand side, you will see that figure 6. And by the way, this is from a reviewed and published paper that I put out, and I have that in the references below. But the higher failure are things like cyclic steam, high pressure, high temperature, corrosive exterior fluids. Those things are all generally field wide. And when you start seeing one, you're going to see others as it goes through this thing. Some of the safest ones down there are the horizontal multi-frac. If they have barriers in the vertical section, you get away from a lot of this problem. So those are at a much lower failure rate. And you see in the center there, the number of wells with barrier element failure. The single most likely type of failure is failure of the connections in the tubular strings, because these 8-round and buttress threads are not gas tight. And over time, they lose the seal. So those are the warning factors, some of the warning factors that you really need to look at. All right, next slide, please. So a completed well, how many barriers? Where a barrier is a pressure barrier, and you have 2 barriers at surface while you're drilling. You might have the drilling mud itself, you might have the casing or the head, the drill head that you're going through, the rams, all of that. Those are barriers, but they're barriers that disappear when you put the well on production. So you need that cement, you need the good casing, and you need it to be selected to actually prevent corrosion, damage, and also it must be high pressure enough to handle everything. But the couplings go right along with all those tubulars. Now you get down at the bottom of the well, you might not have any barriers because you're shooting holes through the pipe to produce the fluid. But go on to an abandonment project, you've got to seal that up and isolate that from being able to even come near the surface or a channel that would lead to the surface. So that's the purpose of the barriers. If your barriers hold, you don't get leaks. Next slide. All right. Now I've I pulled up studies and I've looked over these studies of over 650,000 wells. And in many of these cases, you see, if you look across to the barrier failure frequency range, this is while it's producing or shut in, you're going to see that it's low in terms of percentage. But here's the deal, millions of wells. And you multiply that, and then you still got wells coming up that may leak. So that is an issue. Notice that most of the older wells have a much higher leak rate than the newer wells, the newer era wells. A lot better technology being used, a lot more knowledge about what is going to work and what won't work. And so that is an element that we really need to look at. But yeah, what it says here is you need a lot of information. You need good background on everything that is going in here. But look back at some of these old things, and you can see that when you didn't have a lot of barriers, your cement wasn't good, you're going to have a lot of orphan wells that leak, or shut in wells leak, or even plugged and abandoned wells that develop a leak later. Next slide, please. All right, here's an example of well integrity loss, and this is the Aliso Canyon um, gas storage well out in California. This was a few years ago, about 10 or so. And it was, they used old producing wells to form the injection wells, injection and retrieval wells in this gas storage area. I got the records of this well that was leaking about a day after the well started leaking. I got to look at that, and I found that the well had been drilled in 1954, had two sidetracks, only had 700 feet of cement that I could see from the plans in a well that was thousands of feet deep. And it was just almost what I looked at. My opinion was that I would have never used this well for this. I lived for a time there, about 700 yards away from one of the biggest gas storage area input areas in Texas. And I called them. I had a long conversation with them after this, and I asked him, "Well, what'd you do?" Because I know it was a lot of old wells. He said, "We plugged every one of those old wells. We drilled new wells into there, and we haven't had a problem with leaks." Now, those were some orphan wells that would have given you fits if you didn't know where they were, and they were not plugged and abandoned correctly. So a quick look at all this stuff will find some of the problems that you get into. Next slide, please. All right, now here's a simple plug and abandonment from the internet, and they're talking about a 10 to 25-foot cement plug at the surface and a 100-foot downhole, 50-foot above and 50-foot below the shoe, and all of these. Those are minimums. This would be a good plug and abandon for a low pressure sweet gas well with no corrosion problems and no outside issues of the environment. A very simple one, but it's simplistic. You need to design a plug and abandon in any well, orphan well, shut in well, whatever well, for the environment around it. And that requires a lot of background information. And if you don't have that, you need to spend the money on doing the investigation before you try to do a P&A on any well. And P&As are much, much easier on any well than the repair of a botched plug and abandonment technique. You've got one chance to do it easily and do it well. All right, next slide, please. All right, best plug and abandon, it depends on the well, the field, and the environment that's around it. And you have to come back to the good quality cements and other things. But when it comes to repurposing, and when I was looking through this area of repurposing these wells, last week, I found that several were suggesting you could either use it to store old windmill turbine blades in it, etc. Please don't do that, because if that well ever starts leaking from the plugs below where all this is stored, you're going to have to pull all of that stuff out of there to be able to get down to it. So be very cautious about repurposing any well that's been shut in for a long time. It needs tests, it needs to be investigated. Now, geothermal would have a maybe a project for this or a potential for this, but the tubulars are too small. You have to have very large tubulars to move the amount of water to make a geothermal project efficient and payable. So we just don't have that. And besides that, if you've got a methane leak coming into that old well, you don't want that coming up with your steam and then go to flash it off. It's going to be a disaster. So be cautious about repurposing these older wells, particularly the orphans and the ones that were shut in. Next slide, please. So finding the wells, there's a lot of different ways you can do it. You can look for vegetation problems. You can look for magnetics. You can do the logging deal. There's ways to look for these things, not excellent ways. You won't find all of them, but you can find a lot of them. And it will require some field work to be able to see where these things are. Again, I would go back to my high risk list that I made, and I would look for those first. All right, next slide, please. Now, measuring the methane, that's easy. Finding the source may not be, because of the ones, this methane sources that I've shown here, a lot of them can be from things that don't have anything to do with the well. If you look at the little shot over in the right-hand lower corner, shaded map of California, you can see where their oil and gas fields are, but that area on that whole coast is a very frequent area for gas, natural gas seepage to the surface. So don't confuse that with your orphan wells, because that's not, that natural seepage is not going to be something you're going to be able to really do anything with. So next slide. These natural gas seeps, they're springs and generally from shallow petroleum deposits, but the gas is going to come right up through the soil. The most common contaminant in freshwater is methane gas, which is associated with it almost everywhere. Now, next slide. I'll give you a couple of examples here. This is a map of the world, and the darker sections are your production basins. Now, you take that and then you start looking at the wells. Next slide, please. In the United States, and I've redrawn that graphic, and the red and green areas are the producing zones. So you may have a gas seep which is in the same area as your wells. And so you need to differentiate between the two. And remember, it's the same type of gas. Just getting a sample of it and figuring out that it's a thermal gas versus a natural, recently created gas from cattle, et cetera, the ruminants, that's what you really need to look at and be sure you're in the right area. Otherwise, you'll spend a lot of money that needs to be spent elsewhere. It's going to be wasted. So find your seeps and track it back to your wells. Next slide, please. Now, these are some of the references I've used through this study. This is the end of the two slides. I'll show you the next one. But there are quite a few of them there. I'm going to suggest that you look at that first one. And this is one of my papers presented 12 years ago. And we looked at all of the well integrity issues around that and what wells were most likely to leak, where they were, and what the fluids that were coming to the surface would be consistent of. With that, I'm open to questions and thank you very much.
All right, thank you so much, George. That was a great presentation. We had a couple questions come in the chat, but I think we'll save those for the overall discussion. And Jim Slutz, our co-chair for this study, is going to be our facilitator for this session. So, Jim, I'll turn it to you if you have any questions for now.
Well, what there's a couple, but what I thought we would do is focus maybe because since to kind of get the capture the richness of both speakers, maybe we do a little bit of clarifying questions from the committee, things that people want to ask, just a few. And George, I assume you're available to stay around for this entire section. If so, we'll move to Dwayne shortly, and then we'll come back and we'll have questions that you both can address. Does that work?
Yeah, I'll be around for the morning session.
Okay, sounds great. I'll let's see if we I'll offer the committee if you have questions. I have a couple that I jotted down. One I on your I found that one slide where you were looking at shoe tests and you used Texas, Ohio, and Alberta. And one of the questions and it has to do with some of the issues the committee is looking at, is this availability of data. And I presume that I didn't know if that was you chose those because of their historic background or because the data was available for those, and because we're going to maybe do some surveys of the states and kind of see what is available. But I think I'd be interested in hearing about why you chose those three, and if it is a data availability issue or just other reasons.
It is a data availability issue, and I checked on almost every state that produces. The states that have the least amount of problematic wells, not, they may have a bunch of orphan wells, but the least amount of problematic wells had most of the wells drilled after 1900. And most of those wells were stayed on production for decades. Before 1900s, some of these were, well, most of them were not cemented. Cemented wasn't used till the early 1900s, but the wells in Pennsylvania and the Northeast were rated for scrap metal. They pulled the casing out of it during World War II. And this is an area where those wells are going to be extremely difficult to find, to re-drill, and to really fix. And it's just a point of the era that they were drilled in is just, there was no barriers in there. They weren't thinking about anything. That's time, but that's it.
Yeah, I'll just add I started my career regulating the industry in the state of Ohio, so
Yeah,
I was a bit pleased that that was an example, and somewhat not surprised based on some of my knowledge about in the 1980s when we
mm-hmm.
were kind of figuring out how to create, redo regulations a bit ahead of some of the
Right.
others. Let me go to some others. I have a couple other questions. I might save those till a little later because I think it'll be useful to get both speakers. But let's go. And I'm not sure it's the order on my screen, but Jeff, I think you're up.
Hey, Jim, thank you. George liked it. Context and say my bias. I'm a 20-year cementer, so I like to hear all the comments around how important cement is. I might just do it because I like it, but I like to see the comments there. One thing I've noticed, George, you talk about errors, the error, not errors, but era that we have cemented and how that results in different successes and failures. I have spent most of my career a little bit before the unconventional boom, but now it's been almost 20 years of some of this unconventional cementing and fracking and practices. And our produced water injection has just gotten to massive amounts. And we've seen a lot of stuff in the Permian where failure rates, things are failing at a rate and in a method that I have not seen previously and have changed. Even though our cementing practices increased and we saw failures decrease, now we're seeing failures creep back up due to corrosion. And I'm just wondering if you have, data sets around like, our practices in the past have been good enough, but maybe they need, like you said, we have to stay ahead of what we're trying to do. And if you're going to P&A well, you have to kind of predict what the well will have to protect itself against in the future. And just your comments around that.
Okay. For the last 4 years, I've been working pretty strongly on the the casing failures during the multiple fractured horizontal wells. And what we found there is there's a multitude of things that are happening. One is fracture driven interactions, where one fracture is driven into another wellbore offset just along the regular fracture plane. And on that intercept, it collapsed the pipe or it did something else. This is generally at a low level, a deep level, and it interferes with getting your fracturing plugs down there. But uh, fracturing, multiple fracturing will cause fatigue in these pressure cycles. I mean, it goes from maybe 5 or 6,000 to 14,000 psi pressure for a frac, and then back down in 2 hours to the 5,000 to 8,000, and then back up to the 14 for another frac. And we put as many as well over 100 fracs in some of these 3 mile long horizontal wells that we have. So when you do that, you must take into account the fatigue, the multiple cycling of pressure. Also, you have erosion issues up high in the well, and you have a lot of different pulsating problems down below. And we tried making a database of that. I work in an SPE study group on that. Tried making a database and couldn't get anybody to really contribute enough information. And we're at a point that we had to slow down and finally figure out what information do we need to take to be able to see what's the limit. And, the drillers can push you a well out 40,000 feet from where the wellhead is. But can you actually treat that, use that, etc.? And in many cases, you can't, but some you can. It just all depends there. But there's some information in there that is available today. In fact, I was co-author on one of the papers presented at the Fracturing Forum a year ago, and it was represented at the annual technology conference. So there is a lot of information out there on that.
Okay, thanks, George. We have three additional questions, then we'll switch to Dwayne. So next is David Perrin.
Hey, good morning, George. My name's David Perrin with Chevron, well P&A advisor. I've seen your name on a lot of PowerPoints before, so I appreciate getting the chance to meet you here. Great presentation. My question would be more clarifying. So, we started off talking about just well integrity issues around barriers and barrier elements like the tree valves and tubing connections and things like that, which I think is definitely relevant in a well that's sitting idle or shut in long term. But as far as, you know, post P&A, doing the P&A correctly, um, at least certainly in large pockets of industry, we don't rely on those type of barriers to, for long-term integrity. It's really cement and permanent barrier, full cap rock restoration or rock to rock barrier. So I want to clarify that, and that, well integrity from, not having the right connections or things like that, while can pose a hazard of leakage before you get to the P&A. But after P&A, do we, necessary in your thoughts, rely on that? Or, it's really, we can compensate for, we don't really look at steel casing and tubulars as a long-term barrier, for a millennia or whatever, and permit, in that eternal perspective. So just kind of clarifying that statement.
Okay, and I agree with you there that if you don't rely on steel, if you rely on cement, that's a rock. And a rock to rock barrier is much better than having any pipe in there at all. The pipe gives you an avenue to get in and set everything. And if you've got your plugs in the right area, I know sometimes we have had to just mill out an area of the pipe and then squeeze the cement and put a big plug in there. And that was the only way we could really get an effective barrier. But what I'm talking about here is the linkage between the well integrity to start with and what you have when you want to plug and abandon it. And then if you know all that information, you can go in, you can pull casing, you can mill out casing. But as I mentioned probably 3 or 4 or 5 times, the quality of the cement is the key.
Yeah. No, appreciate it. Thank you.
Okay, thank you. And I have 14,000 PowerPoint slides, by the way.
We're gonna move this, we need to move this to Dwayne pretty soon, so we have sufficient time at both for Dwayne and for some follow-up Q&A for Dwayne and both. But Nathan, go ahead.
Hey, good to see you again, George. Nathan Meehan, Texas A&M. Couple quick questions. You had some statistics that had some relatively low percentage of wells with failures. And I've got questions about that. Is wondering how many of those were actually, did we measure that they had no methane emissions, or did we just not have one reported, so we had no failure? Because it takes a little effort to make a surface measurement of relatively low rates of methane emissions. So,
Right.
and then also, we could also have saltwater or subsurface leakage to another aquifer or from an aquifer to somewhere else without knowing about it. So I'm just wondering why, that it seems like really low rates of leakage, but that number could only go up if we made more measurements, I assume. I'm just wondering how do we get those low numbers, and what does that include in terms of low volume leaks or subsurface leaks?
Right. The low numbers are a direct result of they weren't looking for methane, they were looking for oil leakage. And you have to assume, and I hate doing that there weren't as many methane leaks, but I think there would be more because the pressure from when you've depleted a well, the pressure from outside is much greater than the pressure in the pipe, and you're likely to have leaks coming into the pipe or into the well rather than out of the well, except for the methane which comes up. And if that methane can reach the surface, then it's got a lot less hydrostatic pressure outside of it to push against, and you can have more methane. These, all of these, this Texas, Ohio, Alberta, almost all of those were methane leaks. Alberta went a little bit further and started looking at some information on well leakage in terms of methane. So got some very good papers coming out of Waterloo University. Maurice Dissol. I can't pronounce his name right. Dissol, yeah. And he has some good information on that. And there's several other papers that I've pulled up over the years. But yes, you're going to have more methane leakage than the oil leakage that was put forward in most of these characters. Really good catch. Thank you.
Okay, let's do this we have Walter, and Maleva has her hand up too. Why don't you guys both pose your questions, and then George will let you answer them both. We'll let you do the answers, and that way we can move things a little, since we need to move shortly to our next speaker. So
Yeah.
Walter, you first, and then Maleva, go ahead and
Okay.
pose questions.
Okay, thank you, Jim, because I was going to say I'm happy to defer my questions until later if we need to move ahead.
I can do the same.
Okay, if they're, especially if they maybe apply to both speakers, that's awesome. And just for those that are online, and listening, I know there's questions that you've posed, and we have a number of them that I think we want to bring up to the group, but I think it will be they're ones we can bring up to both speakers later in the session. So we'll do that. And so with that, I guess we'll switch Dwayne to your presentation. We'll do kind of some clarifying specific questions with you, and then we'll get a dialogue on with the committee and both of you, and we'll bring in some of these other questions. So Dwayne, I'll turn it over to you, and if you have slides, we'll let those get up here.
Thank you for that, Jim, and thank you to the committee for inviting me. My perspective is a little different. My discipline's a little different than George's. For 30 years, I've been a reservoir engineer. So my core discipline has to do with the earth and not with the well bores. For the last several years, I've been deeply engaged with the discussions at conferences and the community on identifying leaks and the causes and consequences. So, to be clear, what we are trying to protect is all of the surface water and the usable water, not so much concerned about long-term plugging effects on cross flow from one subsurface zone to another. Although we're not concerned now. I should point out that in the past, we weren't concerned about water that had 5 or 10,000 parts per million solids because that was not usable. But now 3 to 10,000 parts per million of solids is water we do want to protect now. And we are concerned now with integrity about things like CCS injection where we weren't concerned in the past. We ought to bear in mind future optionality when we're designing it. As George said, we generally get one shot. The old rule of thumb is a stitch in time saves 9, or an ounce of prevention is a pound of cure. That's a ratio of 9 to 1 or 16 to 1, and that's probably about right. It is much, much more expensive and difficult to come back and try to fix a well than it is to get it right the first time. The point about the fluids measured at surface is a great point. Of the 3 driving forces that we have in the reservoir, gravity, pressure drop, and capillary pressure, the one that is most important to leaks that we're concerned about to groundwater, surface water, or the air is buoyancy. Always in the reservoir, gravity, expressed as buoyancy, is the most powerful force. And there are certainly places like West Texas in recent years, or Pennsylvania, or California, or Colorado, where we have seen oil move to surface or water moved to surface. But because of the hydrostatic gradient, it's much harder to move oil than gas, much harder to move water than oil. So those will happen most infrequently. The most frequent is the constant, powerful, buoyant force in the reservoir. So and then the question also becomes, when we're talking about leaks, what qualifies as a leak? At what point are we concerned about it, and what point not? We have in the literature about a dozen, 15 studies of emissions from old wells, and those find a very wide variety of leak rates of gas, which is what has primarily been studied in these recent years. And one study I saw a few weeks ago found a leak rate at less than 1%. But there was another study in California, and I forget the population of wells, the status that they were looking at, but it found 65% leak rate. The best data set that I know of has to do with the reporting in Canada of surface casing vent flow. British Columbia allows self-reporting. Alberta, as I recall, requires independent reporting. But surface casing vent flow is a measure of the failure of the cement in the annulus. And as I understood those studies, it was on the order of a quarter of the hundreds of thousands of wells in Canada demonstrated surface casing vent flow, suggesting the most common, if low volume, leak is a microannulus around that cement. Cement is indeed very hard. It's not very sticky. The best, by all accounts, the best way to install it is rock to rock, where you have a rough, tortuous path for it to interface. But of course, cement is still brittle and steel is still corrosive or corrodable. We do see a higher failure rate in older wells than in newer, and there's no doubt about it that we've gotten better at well construction. And it's a great point, borne out by the most recent project by Petroleum Technology Alliance of Canada, that the company doing the work and the person doing the work, that is how you do the work, is a first order variable in how effective it is. It is at least as important as the technology that is used. But at the end of the day, in these conditions, we don't want one other thing to consider. The older wells certainly were earlier technology, but they've also endured a longer time period in the earth and therefore had more opportunity to break. And I don't know of any way to discriminate what higher leak rate is a function of technology during initial construction and what has to do with increased failure over longer time periods of standing idle. But if we do have a small leak, for like a microannulus, it is theoretically possible for the cycling of water level or the movement of fluids or the very minute movement of the earth to exacerbate that issue over time and make it worse. So there's no scenario that I know of in which a leak of gas or oil or water to groundwater or to the surface or to the atmosphere is beneficial. There's no circumstance in which we'd say, hey, that's great. We had a fortunate accident that we got this material to surface. The holes that we drill in the ground are for practical purposes going to be there for the entire future of humanity. If you think of the Copernican uncertainty principle, you could argue that maybe it's only 250 years that we need to plan for, but I sure hope that the future of humanity is at least the 10,000 years that we had before. But in the earth, there is no natural process in most locations and at most depths that will seal off the well bores that we create. There can be sidewall collapse. Now, if we take out the casing, by all accounts, the best thing, we can't have sidewall collapse, where the side of the wall becomes cracked, debris falls, makes it difficult to enter a well. But that doesn't plug a well. That doesn't stop a leak. It makes it difficult to re-enter. There are creeping shales. There are some shales which will slowly move over time and can impinge on the wellbore and possibly in some places, and in some places a salt or an anhydrite that's more ductile can perhaps completely seal the wellbore at one level. But it's not clear that those are going to creep enough, and those are uncommon. They're not at many depths and not in many basins when they do exist. There are places where a wellbore can be sheared off by tectonic movement, in which case you would have a brand new, fabulous restoration of the cap rock, as you say. But the problem is that the environments that can have shear to collapse a wellbore are the same environments that are likely to create integrity issues before the wells get sheared off. So what we're relying on is what we do to the well to last as long as possible, hundreds of years to thousands of years, so that we do not have to re-enter and pay the pound of cure. Now, I heard a distinguished professor yesterday say that in his opinion, we need to monitor all wells, all plugged wells permanently. I've heard the idea before, maybe it has merit, but the concept that he's arguing for is a good point. They can develop leaks. Now, when we're talking about the best practices to stop these leaks, we should bear in mind that the technology that we use today is the same technology that we designed and prescribed 50 years ago. We're using fundamentally the same technology as we were in the 70s, both for what we put in the well, for where we put it, and for how we put it. And I was watching a video from a company earlier this week, and they argued that we were going to, at the end of the well life, fill the well with cement. But that's not true. What we do is to put cement in critical points in the wellbore, but we leave 80 to 90% of the wellbore open, where there's nothing but liquid. So we've taken what was 100% rock and reduced it to 10 or 20% rock, which leaves it much more open, much fewer barriers, less restrictions. In the last 50 years, we have had, as I've observed from an active, engaged member of the industry and a user of these kinds of technologies, a significant improvement, advancement in the additives that we put into cement and the way we design it to get it the properties we want. I have not observed, though, that adhesion, that the connection between cement and rock is a primary variable. As I said, that's the place where we get the largest population of the smallest leaks, and which may be the way it opens up. There is a very wide distribution. So many wells are going to leak nothing. Most will leak nothing within the time period that we have measured them. And then some leak, most that do leak a small amount, and then we have a diminishing tail up to very large catastrophic leaks. But over the last 50 years, we have not had pressure, have not had the impetus to spend a great deal of effort on studying our plugging. The paradigms that we had 50 years ago were, we wanted to, originally, way back in the day, it was to protect the oil reservoirs from the water. But the paradigms were to protect, were simplistic, to protect the surface, to protect people from falling in, to minimize our cost. The standards that we ought to be looking at now, I think, are much tighter. And of course, we have a much more sophisticated understanding of what's happening in the earth. Cement's a great material, but even small movements of the earth can cause it problems. Over the last 50 years, I have seen only one, before about 4 years ago, maybe 3 years ago, I saw only one university lab studying decommissioning, and their project ran out of funding at the end of their initial trial. George pointed out that when he wrote his landmark paper in 2012, he made a review of the literature about well integrity and long-term well integrity, and he showed his citations. There were 8. By comparison, all of the SPE papers in one Petro total nearly 25,000, which is a very, very small proportion of the research was on long-term well integrity during plugging. And what we weren't actively looking at the failure rate. We weren't trying to study this longevity of our wells. Now, and like I said, part of the reason was we didn't have a driver. Part of the driver was part of the lack of driver was didn't need to monitor our wells. We also didn't even need to plug them. Would you show the first slide, please, Jim, or Noel? Starting in the 1980s, in the mid-80s, when the oil price collapsed, regulations systematically changed state by state across the country. Up to that point in Texas, for example, you had 12 months. You could get an extension up to 12 months to plug your well. The basic rule was 3 months. Stop producing, you had 3 months to plug your well. But of course, the states didn't want a mass plugging event. Everyone believed the oil price was going to come back and the wells would come back on production. So the rules were modified and then became permanent some years later, so that wells were, for practical purposes, allowed to stand idle indefinitely. So not only were we not studying, we weren't doing nearly so much plugging as we were before. And at this point, the average unplugged well in the US was drilled around 1985. Now, there's a lot of talk about well counts. And I went back to Enverus and the primary source at States to try to find. Would you back up one, turn off that animation? So thank you. To try to find the population of wells. And this is the conclusion of my work. I've divided it into 3 basic categories. The first is unplugged, the second is plugged, and the third is I don't know. As George said, there's a very long history of drilling and even of abandoning wells before we had records. API numbers were first deployed January 1st, 1967, which is more than 100 years after the Drake well and much more than 100 years after some of the earlier gas wells that were mentioned earlier. Now, the question to the committee is specifically about orphan wells, which currently make up, according to the IOGCC's most recent information last year, 7.4% of the unplugged wells. But in total, unplugged wells are right at 1.9 million. Total wells historically recorded as having been plugged are almost 2 million. But the wells that we have some information about, or the wells that we believe are there, but we don't know about, or that we have some indication were drilled, but we don't know where, number between 1 million and 2 million. And this gives me a total of the 4 to probably the 5 to 5.5 million wells that have ever been drilled in the U.S., the most common headline number. So the wells on the left, advance please. The 7.4% orphan wells are very similar in nature, in quantity, very similar in nature to our non-producing, our micro-producing wells. So the question, of course, to the committee is orphan and abandoned. I don't know of any systematic difference between orphan wells and the majority of other wells, except that we have less information about them in the public record because there's not a viable operator to supply well files. So that does increase the risk on them, but the risk that they present, the risk that they suffer are probably about the same. And this is really startling to me. Notwithstanding the fact that we have the highest oil and gas production of any country in the history of the world, half of the unplugged wells in the country are standing idle, and a large proportion of the wells that are actively produce on average less than 1 barrel of oil per day in 2023, which means taken together that 75% of the unplugged wells in the country account for 0.6% of the production, which is to say the issue is much larger and not systemically different than for orphan wells. One more. Now, in addition, there is this very large population of wells that may develop a leak in the future. Now, we can't do anything about those right now other than monitor, which we can do pretty well if we're willing to spend the money. What we need to, and what we may need to come back to those and fix is a very large liability sitting there and aging. Advance. So thank you for asking, Nathan. BOV is what I call barrel of value. The energy equivalence 6-to-1 ratio that we normally use for equivalency between oil and gas is of no value. No practical applicable value. I use a barrel of value equivalence, a 20-to-1 gas to oil and a 3-to-1 NGL to oil, so that the equivalency is based on the dollars and not on the energy content. You can pause that, pause the display. When there So to deal with these 2 million wells that are still waiting for us, and the fact that we delayed plugging those may prove to be beneficial, because now we have the chance to change the paradigm that we use to plug them. And by all accounts, cement is a good material, a good base material, but we are using it only in a fraction of the wellbore, and it is brittle. There have been some really interesting research on additives to cement, like modified nanopolymers, fly ash to make it a geopolymer, or I recently saw a cement developed under a DARPA grant that was meant to reproduce ancient Roman cement, which has lasted for thousands of years, even under highly corrosive environments. And it could be, all of those are useful, and it could be better. Probably anything is better than neat Class A cement, which is what we've most often used. And there are some really interesting new ideas, such as bismuth plugs. They're probably not cost effective, and indeed, those have often been found to fail. In the Petroleum Technology Alliance of Canada, which I mentioned before, is about to publish a report. They've been studying for the last couple of years in confidential studies a number of these new technologies. And what they found was really interesting and helpful as we design where we're going next. And they started in the lab with a number of products, and a number of products that they tested proved not good enough in the lab to bother testing in the field. And then they did the field tests of a subset of these products, and they found that the field test results did not correlate to the lab test results. From what they did notice, that the person performing the test was a significant factor, a first order variable, as I said, into how well they succeeded. So would you flip to the next slide, please? So that the statement by Alan Fogwell yesterday was that we need better ways to test new technologies for plugging. Now that's grim. We don't even have a good way to test what is a good way to plug. But this graph, this schematic, reproduces his point of key learnings. They figured that in order to have a good long-term plug, you had to have a good product. It had to fit the profile of the well, the nature of the well. It had to be placed in the right place, and it needed to be placed in the right way. It required all four of those, not just a technology, in order to be effective. Blank, please. There's, without getting too much into the technologies, there is one technology that I see discussed too little, and that is a reservoir blocking technology. That is the kind of thing that we would use for water blocking. There are products that are resins, there are products that are gels. Besides the fact that we have cement, there are foams, but there's also some interesting, at least one interesting product that will create a scale in the formation, the kind of scale we have historically not wanted. But to the extent we could block the flow from the perforations, we've blocked it from the source. Now, we do know in the last 50 years that more about the risks that we're trying to protect against. At the surface, we have issues of corrosion. Surface and atmospheric groundwater can be very corrosive, and we have fluid movement through the ground. We have fluid movement inside a wellbore on the outside, up and down. Hydrogeology tells us that groundwater fluid level, or fluid level in groundwater wells, oscillates up and down some with tides. And we know that groundwater can move past it. It can be quite corrosive. From the top to the middle, we have to recognize that the earth is not perfectly stable. I think this was the paradigm for a long time. We do in places, especially like California, where I'm sitting now, we have a natural seismicity that can be even 5, 6, and God forbid 7 on the scale of moment magnitude. But we also have induced seismicity in places historically, like my home in Fort Worth, Oklahoma, and most recently and most significantly in West Texas. And it's that microseismicity and shear waves, compressional waves, but most importantly, the surface waves, that almost certainly threaten to create a breach in the well integrity that can be exploited and exacerbated over time, like a dike that begins to fail and then snowballs. We also have issues in the long term of subsidence, and we may have issues of earth tides. Even a small movement of the earth, especially if the pipe continues to be anchored deep in the earth, could cause very small movements to make a small breach that could be exploited. I am speculating. All I know is that there has been observed a statistical correlation between natural seismicity and the increase of leak rates in a study in Canada. Other issues I don't know, but that's kind of the point. Our old paradigms may not be effective. We've also had the perspective that we only needed to seal against a couple 100 pounds of fluid pressure. But we know now that that's not the case in a number of places. If we have a reservoir like the Delaware Mountain Group that in West Texas that has a choked aquifer, a slow feed in, we can over years and decades see the pressure in the reservoir recharge to or practically to virgin pressure. Slowly, but it get there. And there are other ways that it could possibly recharge. We discovered water flooding in Pennsylvania by accident on a dump flood. Rainwater was going down an unplugged well, pushed into the reservoir, and then pushed oil up another place. And we could see a dynamic like that. There could be some sort of counterflow inside small annuluses in a well that could repressurize, in theory, as a possibility. And we could see situations in which individual wells have a larger issue and they create a dump flood at a larger scale. But more importantly, when it comes to shale reservoirs, we know, as a matter of reservoir engineering, that the wells will repressurize over the lifespan of the plug. We're only taking out between 5 and 15, maybe 20% of the fluid in place in some cases, and therefore, as a rule of thumb, it will eventually, over decades, but within the lifespan of my children, within the lifespan of the plug, repressurize to 80, 90, 95% of its initial pressure. And my personal nightmare is a Haynesville shale well in 2080 that's repressurized to 11,000 pounds and blows out at 20 million cubic feet a day. There are thousands and thousands of wells in the Haynesville shale. Of course, there are other risks that we didn't anticipate, such as massive water disposal and CO2 injection. And these kinds of things may come up in the future. We certainly should protect against them. But we don't know how much they leak or how it develops over time. We can look at seeps in the few locations, the concentrated locations where they exist. We can look at the variability of seeps, and we know from the, at least in some places, they vary with the tides. We can also look at the analog of leaks from landfills, which vary with barometric pressure. And there are probably some dynamics like that that affect wells. We need to understand those by long term. It's because if we can understand the nature of the flow, how it changes, how it varies in the short term, how it changes in the long term, then we can better understand the failures, and then we can protect against those. Jim, do you need me to wrap up? You're on mute.
We would do, I'd take a few minutes to wrap up, but we do want to make sure we have time for discussion and questions, Dwayne.
Super. I appreciate it. I'll focus. So what I think we need is we do need some longer term monitoring. We ought to talk about doing downhole monitoring to look for where and how things are failing downhole. We should be looking at groundwater in a proactive way. We probably ought to have a lab that looks at vertical flow in a plugged wellbore, the same way that we have historically looked at the modes of wellbore tubular flow. We ought to have a frac focus kind of database for plugging. But most importantly, I would really like to see operators reporting on casing integrity failures. In Texas, we are not required to report when we have a well integrity failure, such as a hole in casing. If we had reporting on the well integrity failures of active wells, we have a much better sense about where the risks are. In general, I do think we need a new concept, something that recognizes the variation of geology, the variation over time, the durability of what we need to create. The idea of restoring the caprock is a great idea, but it is still only a single barrier, and it's not awesome. It's much more like a cork than it is a tire patch, a tire seal. It has the ability to fail around the edges. But basic safety principles say that we need more than a single point of failure. Basic principle is that we need multiple layers. And we do, at this point, have several layers. But if we're going to look at the Earth as a model, we'll use the biomimicry model, I believe there's a lot to be said for multiple layers of separate materials with different properties so that we could see something synergistic. I don't believe that we're going to get to the point where a single product will solve the problem. It's really hard to imagine a cheaper product than cement, maybe a more effective product, but I believe that the most effective is going to be a combination of materials with different properties. Now the best way to reduce costs, I believe, is going to be not a cheaper material, but a different process. So instead of a one rig, a pullover rig continuously, what we do instead is a different process where we come in at stages. Would you throw up that last slide? Oh no, one more, next one. All the way to the map. The biggest problem that we have, I should say, as an aside, is not the technology, it's not the materials, and it's not the process. We have ways to improve both of those. The biggest issue is the money. In back of the envelope calculation, the dark blue states are states where it's not practical for the wells in the state to supply enough money by a fee to cover the plugging of their own wells. And the light blue are places where there certainly is enough new production. Let's pause that. Go ahead and go to the last slide. I'd encourage you that the oil industry is anti-fragile. It's a great candidate for the Porter hypothesis. But you can go to the last page. The oil industry is a great candidate for the Porter hypothesis. We have done what we've done without testing how systematically how reliable it is, but we will respond to requirements. When the standard is raised, the oil industry will innovate. We'll find better, cheaper ways to get the work done. And we will be stronger and more competitive as a consequence of raising the standards over our 50-year-old paradigms. Thank you.
Thanks, Dwayne. We will go over a little bit here so we can have time for discussion. So why don't we, just in the interest, since that I kind of Walter and Maleva kind of put off their questions, and I know they may be specific to George, but we'll kind of move more to the joint dialogue, given time. And Walter, I think you were up, and you can let us know if you want to direct that more to Dwayne or George.
Okay, great. Thank you, Jim. Hello, my name is Walter Guidros. I'm a geologist, formerly with Amoco, NBP, and most recently the USGS. And my question was originally intended to George, but I'll pose this to both George and Dwayne. I know we've talked a lot about early wells and the failures associated with those. I'm just wondering, from a geological perspective, when you consider that many of those wells were drilled in relatively simple geologic structures, in other words, many of them may not have been heavily faulted, they may not have been proximal to faults or perhaps even drilling through salt. Would that have an impact on perhaps later wells? And could later wells perhaps be considered to be more at risk because the geology was more challenging, operators were willing to kind of push the boundaries a bit? You may argue perhaps that could be mitigated by improved seismic technologies or perhaps better geologic data. But I'm just wondering if you might have a perspective either from the data or perhaps your own point of view as to whether or not there might be a historical perspective that could be looked at in terms of kind of the prism of how those wells or when those wells were drilled.
Okay. I have a perfect example of that over in Sichuan, China. We've worked on wells over there with a very, very high failure rate of the wells themselves. I don't have anything on the P&A there, but I do have the difference between what we're seeing in casing damage during completion of a well. We might have 1 in 10 or 15 wells that has that. In China, 40% of the wells in this highly seismically active area do have that problem. So you're dead on with problems really coming in when you're drilling in other than just almost a powder puff formation. You're going to have problems.
Yeah.
All right, that percentage, did you say 40%? I couldn't quite make that up.
40% of the wells have at least one damage area following completion.
Yeah. Well,
Right.
so you're talking about initial conditions, George, right? Initial quality.
Initial conditions, yes.
So you're
Scary.
in here in Bakersfield, also unique soft formation in the Bellridge diatomite. The old rule of thumb when I worked on it in the 90s was that you were going to lose 10% of your active well population every year to wellbore collapse. Now that's extraordinary. That's unusual. You get into hard rock country in Montana, it's a different story. But it's certainly true that we weren't cementing at all. We weren't drilling very deeply. A friend gave me this little volume from 1919. It's on state of the art in petroleum geology, and they're talking about how it is possible to produce from faults, but it's really dangerous. But the most reliable indicator is a surface hell, right? Um, and the deeper we go, the harsher environment we're exposed to, and the more potential zones for stress we're exposed to. So there, all those dynamics are true, and we have historically allowed regulators to create one standard per one prescriptive standard per state. But even within the states, we get some radically different geologies. Colorado has 8 or 9 productive basins with some widely different conditions. Best practices are probably going to be principle based, not prescriptive.
Thank you.
Okay, Maleva.
Okay, so how to combine something? What got my attention is in the first presentation, George mentioned that quite a few of these failures are associated with when there is a boom, when there is a lot of activity. And it's logical, we start to cut corners when we don't have enough time. And so looking at, energy transition and how subsurface is going to be used, as Dwayne mentioned, for CO2 storage, for geothermal, for, I don't know, hydrogen. There seems to be a lot of activities that, we are planning for subsurface. And so, I mean, if you had to pick one major shift that you would like to see, this is to both speakers, what would that be? Because you mentioned lots of stuff, like from experience of the crew to different technologies, etc. But like you prepared for these presentations, and you clearly looked at much wider picture. And we have I didn't really know this, 5.5 million wells ever drilled in the US, approximately. That's a lot of wells. And according to these numbers, we'll be doing P&A for quite some time, even if we're not to drill a single well. So, sorry, that's a little bit long.
George, what's your wish list?
I'd like to have enough information to know what's going on down there.
Spoken like a true engineer. That's 50 years of engineering talking. We can't. We need data.
We're 1 to 5 miles away from what we work with. You can't see it, you can't hear it, you can't touch it, you can't taste it, and you don't want to smell it. So what do we know about it? I mean, come on. We're
Yeah, yeah,
taking minimum data just to be able to drill the well
yeah, yeah.
faster, but not data on how to make the wells last.
Yeah, yeah.
That's
So
the biggest problem.
and that's a great point. We really need to start there. We accumulating a data set that can be used, a very large data set we can use to look for patterns. And we need to make sure we preserve old data like log libraries and well files from operators that are going out of business. Those are going to be precious. It's absolutely irreplaceable. If I were going to prescribe what would happen, I'd like to see a centralized research center, to try to figure these things out, to collect the data and collect best practices. I'd like to see them running a training center on how to physically do, so we have good operators out there on the rigs. But in terms of design, I really believe that our best solution is going to be something that fills much more of the wellbore, and it could be with bentonite or Leda clay or something else. But if we have a variety of properties and we fill most of the wellbore with a rock to rock, if we take out the casing, I think we're going to end up with something that's much, much more resilient, and we won't have to come back in and re-enter it. Less likely to have to come back in and re-enter it.
I'm going to push back on that just a little bit here. I
Oh,
agree with
please do.
what you said. Is I heard that somebody wants to fill the entire wellbore up with cement. I think that's a mistake because
Yep,
if
I
you
agree with that.
do get a leak, no matter if it comes to the surface, etc., if
Yeah,
you have a pathway that you can check pressure, flows, material that's coming out of there, you've got a
yeah,
pathway to fix it. And this is why I push back on total cement.
yep,
But
yep.
I agree, man. I'd love to see some, forever cement because cement does have a 3% shrinkage deal when it's in the well. Now, you can have expanding cement. Most people don't use it, but you depend on those shales to push in and do the seal. Real good paper on that, again, by Maurice Dussault at Waterloo, and he looked at that and found that over a period of 30 days after you drilled a brand new well, you'd see methane coming up from the soil around the well, released from the wherever down there. Over 30 days, that goes down to zero as the earth, shales, clay, everything clamp around that at outside casing.
Yeah.
But you got to
They,
remember that one thing. It's if the earth moves, the pipe loses. And that's
oh,
salt, that's shale, that's anything there.
yeah. I, I think I can make a bumper sticker out of that. But I would, if the
It
earth
wasn't
moves,
mine.
the earth moves, the well loses. But you're right. If we, all cement's not a good idea. But if we had elements of good, well-designed cement and other materials. So one of the
I
things
agree.
that this yeah, super. Well, this one lab that I was talking about put a plug in place, and then they put a hopper over the well with bentonite chunks, and they would feed some bentonite chunks into it slowly over time because bentonite would swell, and you need it to solidify before you create too much pressure. So they could fill it up at a very low cost, slowly and securely, using a hopper. So if you loaded up a hopper with ground up waste concrete and bentonite, and then dumped several feet or tens of feet over time, and then came back and put in with even a dump baler maybe some cement, and then we went back. I think we could fill the whole well up slowly and cheaply. I'm I'm getting out of my domain here, though. I'm just positing a possibility.
So I'll tell you what, we will put on our list because I heard this a little bit and I had it on my list of questions too. This idea of the material between cement plugs may be an area that we should, and because I know different regulatory systems have different requirements for those. Some actually do require a certain weight mud and things like that. But I think it sounds like that's something we should put on our list. And I just reference that because we're gonna kind of move to David Perrin and his question on that or his question not on that but moving along here on the discussion.
Yeah, no, thanks. It's been very we definitely filled up the full hour, right? Or hour and a half. So it's been a very good discussion. I appreciate it. Good insight. And maybe this is a question for both of you. There is, I'm not saying I advocate for this or not. There's some line of thinking is, well, if you have a well that doesn't, let's say the unicorn has no well integrity issues, has no surface casing vent flow, and has been producing like that for 20 or so years, to default to what George kind of just Googled a P&A procedure or whatever is the minimum standard for that, state or section, would you default to that and take that, obviously if the annular cement has not shown leakage in this, the production life of the well, is that satisfactory or not? And I'm not picking sides or not. I just would like to get opinions on those those two things. One thing is if you have sufficient evidence that the well has a problem. But what about the wells that or maybe more cookie cutter? How you take
I
that
would I would
thought?
take that I would take that as a good indicator, and I would press here for a way to monitor,
Okay.
at least for X number of years. And I think that will vary with where you are, what you're doing, how much pressure are you dealing with. There's a lot of things in there. So I need information. I just that's that's just a problem we seem to have.
Yeah.
Yeah. Yeah, I'd love to see it. I second what George said. I'd love to see us with what I call a body farm. I'd love to see us plug some wells with fiber and monitor them long term like we would a producing well.
Okay. Okay, we'll move on to Eilers.
Hey, thank you both for your presentations. Actually, I do like that you mentioned that you wouldn't recommend filling the well fully with cement. We've done a little bit of research in that area and looking at like if the bentonite is placed between the cement plugs, and I think that's really promising for multiple reasons. That it supports cement hydration and placement where it's intended, but you definitely need to make sure the properties of whatever material is placed between the cement is sufficient to support the cement. And I also think, in terms of re-entry, that would be, make it possible to re-enter the well. I did have a question. Do you know, like, where or why you're there? They just prescribe placing cement in it's usually producing zones and freshwater zones, things like that, and don't necessarily have something between the cement plugs.
Well, you're going to have communication within the top and the bottom unless you've got a very uh, well, you've almost got wedges of impenetrable material in there, or slowly penetrable material. But I don't think it's a major interest to put cement over the whole zone if you want to go back sometime and maybe repurpose this one into a producing well again. And that may be where this comes from. But if I can get down to that producing zone, I could do some testing, see what's there. But I can't give you an advantage or a disadvantage to putting cement between the top and the bottom. It's just a bunch of guesses is all.
So you said putting cement between the top and the bottom. Did you mean putting bentonite between the cement plugs?
I mean, I was just wondering where, because I looked at some of the state codes. I was just wondering where that came from. It seems like it's common practice that they don't fully fill the well.
Right.
So you think it's because they might want to reproduce. I mean, I heard some of that anecdotally, but I wasn't quite sure where that came from. And yeah.
I'm not either.
Where we have prescribed to put the plugs are places where at the point where we think the most important leaks would happen. Consistently, we have them over the perfs, we have them at the base of fresh water, and almost universally at the top of the well. We don't want people falling in. We don't want water coming in or out. We don't want water moving up into what we have historically called fresh water, and we want to stop the fluids where it starts. I think we've put the cement at the structurally most important points. But as why we didn't prescribe more, I don't know. I think it was just that we thought cement was a permanent material, and we thought we weren't ever going to use them again, and we weren't worried about and didn't know about the small risks that might develop over time. Structurally, I like where the regulators put cement plugs. George, would you agree with that?
Yes.
I I did have one more question. So I think maybe it's Dwayne, you were mentioned, like having a better lab. What would you, I mean, in my mind, I think we want to best represent the subsurface conditions as we can, but do you have any specifics in mind
I would do a
or
couple
recommendations?
things.
Yeah.
Yeah, sure. First, we already have labs that we've used to study vertical flow in pipes, where you take a functionally something like a an elevator shaft, and you can stand up tens of feet of vertical flow. We can repurpose those, put cement on them, and then bang on them or expose them to something and see what happens. We need to do field tests in real life field conditions. This is the concept that I call body farm. Let's take a group of wells subject to high stress conditions. Let's look at the way old historically plugged wells are leaking or not, and then let's try new technologies and existing technologies with fiber or some other sort of sensing from deep in the well, so we can watch it both subsurface and surface and see how they age. But in the short term, the best thing that we can do is large cohesive, integrated data sets. That's the reason I'd like to supplement that with reports by the regulator to the regulators anytime you have a breach of integrity.
What about plugging? Like when they're plugging, I think because in my mind, I think that's also a lack of data that would be very helpful so that we can start. So you have a large data
Yes.
set. We have all these wells that are going
Yes.
to be plugged. Like let's collect a comprehensive data set on as much information we know about that well, plus how it was plugged.
And exactly, that's what I meant when I said a frac focus for plugging. This is a place for operators to report what they found and what they did. So they would say, for example, we found a problem at 1900 feet. And then once you accumulate a bunch of these operators' records, we can see that there is a pattern of well integrity loss. So when I go to plug my well, I can look at the experience of everybody else and figure out what I'm likely to encounter, and I can make a better design and a more cost-efficient plan. I think that is a practical idea that can be accomplished without giving away competitive advantage.
I think too, like consistent information, so that
Yes,
everybody is
it has to.
collecting the same information,
Yep.
so it's comparable. And I think you
Yes.
could gain a lot of information when you do like large data analytics on it. And
That's right. The data needs to be
like that.
very carefully structured so that it's open-ended enough but consistent enough. I believe that we can do that. I believe that we have enough knowledge of databases, enough knowledge of the issues that a database could be structured that gave both flexibility and enough structure to be useful for analysis.
Okay, thanks. We kind of
Thank you.
we keep moving. So Nathan, I'm going to move to Nathan.
Right, yeah. So, Dwayne, one of the things that we learned last year in the workshop, that this is studies kind of a follow-on to, and was a little bit of a surprise to me, was how consistent the state rules were. I was expecting some variability, but there wasn't much. And you identified where those structural things were. I'd say that liner tops were also covered by almost all. Yeah, that's the one you left out.
Liner tops and flow and zones that are known to contribute flow.
Known problematic flows. So then that might reflect some regional issues. But they were also fairly consistent in not having any requirements for monitoring. And so what I'd like to, you both have mentioned it, we don't really know of many subsurface monitoring things for downhole leaks and saltwater, freshwater, or even hydrocarbons from one zone to the other. We don't really have much technology there. And we certainly have some technologies, a variety of them for surface leaks, but we're not. I'm going to boldly predict that we will not monitor all plugged wells. And since we now monitor hardly any, what would you think in terms of suggestions? I mean, surely we could prioritize some wells that say, these are the kind of wells that
Yes.
will require some monitoring. What kind of ideas do you have there? Thoughts? And maybe it more just needs more work, but do you have any ideas off the top of your head? What wells should we monitor?
Risk ones mainly. And I think that this will come out when everything is settled, if it ever does. It would come out that, that deal when we started looking at methane leakage in a field over a large area, we found that a very high percentage of the methane leaks come from a very low percentage of facilities there that included both wells and compressors and gas reformers. There's a lot of different things there, but we look at the major ones first, and those definitely need to be monitored.
The only thing I'd add to that is that we ought to monitor places also where we think there's low risk. When the scientists were first starting to study sleep, they only watched people sleep for a couple of hours. And they said, this is plain, nothing's happening, nothing happens during sleep. They didn't watch long enough to see REM sleep, which is qualitatively different. If we only monitor areas where we believe there's risk, we won't learn anything about the places that we assumed, interpreted at low risk. So it doesn't take a large sample, and long-term monitoring does have a cost, isn't particularly costly.
Okay, thanks. Jim Bolander, your hand was up and you took it down. I didn't want to miss you. So Jim, did you have a question? And then we'll go to Mary.
No, it was just to clarify what Nathan had mentioned about certain states requiring corrosive and other zones, potential flow zones to be isolated as well, not just the freshwater and produced intervals.
Okay, thanks, Jim. Mary?
Hi, thank you for your interesting presentation. This is Mary Tang from McGill University. Hi. So I wanted to ask about, monitoring, we can't monitor all the wells. How many should we monitor and how should we select which ones to monitor? It's the same question as before, but I think, there's a selection piece, but how many is enough? I think that's another big question.
I would look at the risks of environmental risk and the environmental impact of losing large amounts. In areas where you have generally successful plugging, I would give that a light monitoring. You check that every once in a while. If you're in an area where you have, for instance, sour gas, high pressures, etc., I'd like to have more monitoring in that area. And along with that, a quick response is how do you handle it in that particular area?
Yeah, so there are two parts to the question. One is, and George alluded to it, one is how many, and the other is how often. Third part is how you measure it. But all we have to do to monitor a well initially is a yes, no. Is it here? Is there gas, most likely, here? And then you can apply others. We don't know how frequently to test. We don't know the optimal times to test until we understand how emissions evolve with, for example, the tidal cycles, or particularly the diurnal, but other tidal cycles as well. Once we have a better idea of when and how for a yes, no, then we could have a better idea how frequently we'd need to test. But statistics could tell us how many wells we need to check in order to identify a certain percentage of the population that's leaking. So it's straightforward statistics to say, for example, if we think there's a 4% probability of a well leaking at any time, then we have to measure X number of wells to test that thesis.
Okay. Maleva, you're going to be our last committee questioner in this session, and then I'm gonna wrap up with summarizing some of the online questions, and we'll kind of close out this session in the next few minutes.
Thank you, Jim. So as someone who is in teaching profession, I thought I'll maybe ask this of both speakers. It was mentioned that there is a clear, evidence that inexperience or inadequate training is a major contributor in not having wellbore construction in the first place done properly or P&A. So between you two, you have something like 80 years of experience. So what have you observed as the most maybe often missed points in terms of training and that human factor in all of this? And I believe this is going to get even more complex as more of AI gets into the human performance as well. Thank you.
I can sum that up pretty easily. We highly train our engineers, geophysicists, geologists, highly trained. We don't really give any preferential training to the field folks that are running this system. And that that is just an error.
Yeah, I totally agree with that.
Okay. What I'd like to do just as kind of wrap up, and I'm going to summarize a little bit of the themes of some of the questions because of time. And I want to point out a couple because some of the questions actually are very that you George and Dwayne, you may have some input, but I also want to point out, for instance, there's questions about standards and standard setting. And we're gonna I think we have tomorrow somebody from API's standard setting part of the operation, and and many of the regulations reference those kind of industry standards. So I think that one, and there was some questions on regulatory consistency, which was mentioned. And tomorrow we have a member of our committee that is a state regulator, and a couple of us are past state regulators. And so I grit my teeth not to chime in as the moderator on some of that, um, but I think there's some and number one, I want to point out for the audience that submits questions is even if you don't feel like we have directly answered your question is very helpful because it helps us kind of look at questions we should be asking, and will be that information the content of that question carries forward even if we don't get to it today. So three themes that we have touched on. One is all the different regulatory requirements, and should there be one, and maybe a little bit of your thoughts on why some of those are different. And we've touched on those with things like history and stuff like that as well. Another on the industry standards and new technology and implementing new technology. And the third, which I think we a bit touched on, but I think there were a couple questions on alternate use of wells. And we talked about geothermal, and we talked about natural gas storage, but also the issue was raised on recovering minerals from brines and things like that that could be a future use. So what I'm going to just in wrapping that up and giving each of you kind of a last 1 minute or so to kind of give any final thoughts, and if you wish or able to address any of those topics, feel free, and then whatever your wrap up is. And we'll George, I'll let you go first.
It'll be short. Basically, I'm looking at this, and I do propose here that the principle of plugging a well, the principles that you're using, that should be uniform. The individual treatments depend on whether you have deep wells, shallow groundwater, deep groundwater, no groundwater. etc. It's there's too many deals, and if you make this a one size fits all, it's going to cost the small operators a huge amount of money, and they're just not going to be able to do it.
Yeah.
That's it.
Okay,
Yeah.
Wayne?
Paying, I agree with the principle-based solution, right? Not as prescriptive, and even whatever the committee recommends as principles ought to have the ability to adapt, ought to include some ability to adapt, because I don't know that we can outline all the principles. We don't know that we know enough to outline all the principles. And there's certainly companies that are not going to be able to pay for their decommissioning, no matter what it is, even if the standards didn't change. We're going to have to solve the problem. It doesn't matter what we recommend if we don't have the money to do it. The bigger problem is not the tech. The bigger problem is the money. When it comes to, let me just leave it there.
And this committee is focused on the technology side of this,
I know.
how best to do that. So just to clarify, and just for those in the audience, we realize when you look at this stuff, one of the challenges is coming with what are some common understandings of what we're talking about when we're talking about an orphan well, and that's some of, because you get into legal versus technical definitions and all that. So that's something the committee's going to figure out how to make sure that when we address this, we're doing kind of an apples to apples kind of or pick something so we can be clear what we're talking about to the extent possible. Gentlemen, George and Dwayne, thank you so much for joining us this morning. This was a really great kickoff to this initial information gathering for this National Academy's effort. We're gonna switch and have a lunch break. Noel, is there any logistics other than telling people to make sure to return at 12:30 p.m. Eastern time?
That's correct. You've got it, Jim. We'll leave this webinar Zoom session running. Over lunch, we'll just put up a pause screen and then, yeah, just jump back in at 12:30 Eastern time. And Dwayne noted to us in the chat, you wanted to state for the record a correction on
Yes.
a statistic presented. You can go ahead and do that now and it'll be in the recording.
Thank you, Noel. I appreciate that. So I said that I've understood from the presentation, something I understood from the presentation yesterday about surface casing vent flow in Canada. I emailed the author and I got a reply back while we were talking. He said that the high side is about 28% among gas wells, but across the population as a whole, among unplugged gas wells, they see 10 to 15% with surface casing vent flow, but the average for oil wells, which are going to have less gas pressure, is below 10%. So still, it's not as high as I said.
Thank you, Dwayne. I appreciate that clarification.
Thank you.
And thank you for reaching out to the author. That's great. You got such a quick response.
Indeed.
All right. Well, yeah, welcome, Luke. Thank you everyone for joining us again for the afternoon session today. Let's go ahead and jump right in. This is our plugging practices and failures session. Missy Feely, our other co-chair, will be the facilitator for the discussion and Q&A portion. So Luke, if you want to kick it off with a brief introduction of yourself while we pull up the PDF that you shared with us, that'd be great.
Sure. Thank you to the National Academy and to the committee for inviting me to speak today amongst such other distinguished people like Dwayne and George. It's a real honor. I am a third generation well plugging contractor. I'm the CEO of a company called Plants and Goodwin that was started by my grandfather in 1970. Probably plugged few hundred, if not over 1,000 wells at this point, that range everywhere from modern horizontal shale gas wells all the way back to the wells that George was describing earlier this morning, drilled in the 1800s, no cement, wooden conductor and casing in them. And so quite a range of challenges and skill sets that it takes to properly decommission those sorts of things. So what I really wanted to bring up today is I'm sure many of you have been at around the conference circles and everything that have been talking about the issues of plugging orphan wells, and I certainly have myself. And this topic kind of always gets brought up is like, what's the best plugging practice? Like, what's causing all the failures out there? And usually what you end up seeing is some slide deck that shows an orphan well in a stream, and then there's an orphan well in a parking lot, and then there's an orphan well that somebody has retrofitted into a slide that the kids are climbing up and sliding down at their playground, right? And like, cool, right? We're seeing these case studies of how you retrofitted a workover unit to go out there and be able to work under these high voltage electric lines and address that well. The problem is that while good for education purposes for people that have no concept of just how big this problem is and how close many people eat, sleep, and work next to these wells, those case studies are not like scalable. There's no real, like, you're not going to address 3 million wells by talking about all of these idiosyncratic cases that are out there. So I wanted to take a little bit of a different track today and really sort of unpack, first of all, a philosophical framework that I think we all need to get our hands around as policymakers or people who are thinking about this problem and how to get our hands around it and address it. And I think until we can figure out what we're actually solving for, telling you how we should be placing cement plugs is useless. And so the first sort of thought that we need to come to grips with is, what does it mean to plug a well? What is permanence? Is our idea of permanence that this well will remain? Well, let's back up. My understanding of plugging a well is that we've placed barrier materials in an annulus that has stopped the vertical movement of fluids, that being oil, gas, or brine, in an annulus from happening. Now, you could also argue maybe we want to stop the horizontal movement of those fluids as well. But the problem with that definition is there is no time frame to it. And so I guess it has to be assumed that it's eternal once that's done. I'm not sure if that's a fair assumption or not. Secondly here, we don't have any data of what causes P&A failures. Is it the material? Is it the material placement? Is it the wellbore condition in which the material and the placement was done? Is it seismicity? Is it a formation that when the well was plugged was relatively dormant, but due to nearby disposal activity has now caused it to become overpressurized? There is no way to do a root cause analysis because of all of these dynamic factors that are at play right now. The other thing, and I think George sort of alluded to it in his presentation this morning, is that there's not a lot of incentive for stakeholders to turn over the information about how many wells that they've plugged have failed. And that includes E&Ps, that includes regulators, that includes contractors. Nobody who is involved in the process currently has anything to gain by telling you what the failure rate is on their plugging jobs. And so because of that, it's going to be very difficult to come across a good, rich, robust data set in order to do any of this root cause analysis on how we can make the process better. And finally, I think we need to think, again, if we're talking about what does it mean to plug a well, just let's think of a hypothetical situation where, and we'll use methane as an example because it's quantifiable and it's the hot topic that everybody's thinking about. If an orphan well is leaking, let's say 12 kilograms of CH4 per hour, and we go in there and we plug that well and it goes to zero. But 5 years later, we find that it's leaking 12 grams of methane per hour. So a 1,000-fold reduction, but the well is leaking. Do we re-enter that well to make it zero again? The well isn't a plug, is plugged by the regulatory standards that are out there right now. But is it plugged? I don't know. It's sort of like Schrodinger's plugged well, right? Many of the wells that are out there are both plugged and unplugged at the same time, depending on how you look at it. And so I don't think until we have a good come to Jesus moment about what we're actually willing to do to make emissions zero, make groundwater contamination zero, that we can really have an honest discussion about what we need to do to make the process better. So that all comes into what is the cost benefit analysis that's being done on P&A right now. I can tell you that I have spent millions of dollars of taxpayer money trying to achieve TD of an orphan well. So I have a well record. We don't even know if it's the well record to the well that I'm set up on right now. But this well record says that this well is 2,500 feet deep. We've gotten to 1850, let's say, but the well has collapsed. It's caved in over years of deterioration. I'm below the surface casing shoe. The well is not producing any brine, any oil, any gas. I have been set up on that well in this scenario for weeks of additional rig time to get to 2,500 feet because that's what the regulation says we have to do. We have to try to get to 2,500 feet at all cost. And so until we can bring in some more objective decision making to this that does have real cost benefit analysis built into it, these decisions are going to continue to be arbitrary, and we're going to continue to spend dollars where they shouldn't be spent. And so I already sort of talked about quantifying damages to like groundwater, air quality, land value. These are all things methane at least now has sort of a market value because it's been priced in voluntary offset markets. So we can sort of come up with a dollar figure for that externality. We haven't figured out how to do it for these other things yet. But my last sort of tongue-in-cheek point on the philosophical side of things is if P&A companies start turning a profit, have we lost our way as a society? So to give you the idea of what I'm saying there, if you look at, I'm one of the larger plugging companies in the country right now. If you look at my operating profits for the last 7 years, that's EBIT, earnings before interest and taxes, I have been in the black exactly 1 year. If you look at EBITDA, which is earnings before interest, taxes, depreciation, and amortization, so we don't factor in the wear and tear of my equipment, I am break even for 5 of those years, and I'm profitable for 2. What that tells you is that I am unable to reinvest in the equipment that I have right now, let alone scale that business. This is a business that is unattractive to institutional capital because they can't achieve a return on it, which is why well over 90% of any orphan well plugging companies out there are lifestyle businesses. They are not investable entities. And of course, sort of like intuitively, you could think of this, right? We know who the rich wildcatters are. We know of names like Harold Hamm and T. Boone Pickens. We know who wealthy like oil field service magnates are. Our current Secretary of Energy, Chris Wright, I think he has a net worth of over $100 million. But I would implore you to think of a wealthy well plugger that you know, because they don't exist. So if we can't keep up with the current inventory that we have, the 3.5 million orphaned, abandoned, and idle wells that are out there, and if we have to say that P&A costs cannot go up, then we have to accept that we're never going to catch up, that we're never going to address the problem. So what could be actionable on this? I think the procurement process across the board, whether it's at the state level, and I don't care if it's Pennsylvania, Colorado, Texas, at the federal level, BLM, I've seen every plugging procurement RFP that's ever been pushed out by any of these institutions. They're all fundamentally broken. There's really only 2 methods for putting this work out for bid, and those are fixed fee contracts and time and materials contracts. So a fixed fee contract is just what it sounds like. You come out, look at this orphan well or this package of wells, you give a flat price to plug these to the standards that are in place, and that's all you're going to get paid at the end of the day. So you bear all the risk as the contractor. In economics, in game theory, there's this thing called the winner's curse, right? Where like once you get, I believe it's 5 participants in any sort of like low or high bid auction like this, the winner of the auction is guaranteed to have negative value. So if you've underbid a contract, what is the incentive structure that's been put here? Well, it's you got to cut corners to at least try to break even on that project. So classic examples of cutting corners would be like if I produced some water off of this plugging job that I needed to take to a treatment facility. Well, trucking costs are expensive, disposal costs are expensive. Maybe my tank magically springs a leak overnight and it's empty in the morning when I come back out to go to work, right? Um, there are systems for mixing and pumping cement that are very sophisticated that everybody uses when we're cementing new casing in wells because we need, top of the line equipment that has densitometers and data acquisition systems so we know exactly what the consistency of this slurry is that we're pumping down the well. You're not going to be using something like that on a plugging job. You need something much more crude and rudimentary in order to win these bids. And you're not going to be maintaining like your workover equipment to sort of API standards. You're not getting pull tests done on your cables. You're not doing non-destructive testing on your elevators and bales. You're not getting these Cat 3 and Cat 4 API level inspections on your rigs. You're putting workers at risk by not doing that. And ultimately, you're not delivering the product I think that as a society we should all want. So I think everyone can sort of understand how fixed fee issues create some pretty poor incentives. Or in the best case scenario, I guess, everything gets done to the standard and the winner realizes that negative value from winning this contract and they eventually get forced out of business. So like that's sort of the optimal way that this happens. The state gets things done cheaply, and the person who took the risk on bears the brunt of it. The time and materials contracts out there, I know Texas does this, they still are problematic because they contain price caps that are based on historical data. And I think, as maybe George and Dwayne have already talked about today, we can't continue to operate under a historical paradigm if we expect better results from how we've always done things. So the way those contracts typically work is you provide unit rates, but if those unit rates, if your hourly rate that it costs you to run a rig or run a wireline truck or a cement truck is too high, you are not going to be doing that orphan well work. And you can look at any of the blue chip oil field service companies out there, Ranger, Axis, Halliburton, SLB. None of them participate in orphan well plugging programs. The one exception might be Key Energy Services. I know Key is doing a lot of orphan well stuff in California. And probably not coincidentally, the average cost of plugging orphan wells in California is at like $186,000 each right now. So there's just not enough juice to squeeze out of this fruit for serious scaled contractors to want to be involved in it. So I guess my conclusion to this would be if you want the cheapest price, don't expect a first class product. The second point here that I think is actionable is that there is no true audit trail for any of this work. So I think it's fairly well known that there are not enough oil and gas inspectors out there to be present on every plugging job that takes place. Again, the Railroad Commission will tell you that there is an inspector on every orphan well job that they do through their program. I think at any given time they have like 11 rigs running. But if you ask them about what about marginal wells, many cases they'll say, yeah, an inspector never steps foot on the site of a marginal well that got plugged. And a marginal well that got plugged and then that marginal well producer that eventually goes out of business, that's an orphan zombie well potentially coming forward, right? And so there's not enough inspectors out there right now. On top of that, many of the inspectors don't have the experience or the industry knowledge to ask the right questions. The Texas Independent Producers and Royalty Owners Association cited in their latest State of Energy report that the average salary of an employee classified as being a part of natural gas extraction makes $176,800 per year. Now, I don't know what our average civil servants are making out there working for the various regulatory agencies, but I don't think they're making that kind of scratch. And so if you do have the ability to really know what's happening at these subsurface things and you're really skilled at it, you're probably not working in these agencies to begin with. And so there's a real asymmetry of knowledge that's out there. And that can be tough, especially if you're trying to scale up the base of oil and gas inspectors available to look at this work. You're going to have to bring in a lot of inexperienced people to do it. And so then did you actually accomplish anything if they can be tricked or they don't know how to ask the right questions when they're on site? And the real problem here is, like it's been said already this morning, is that there's just no proof of work except for a plugging affidavit that gets signed at the end of the job. Like let's say if I'm doing a addition on my house and the code inspector decides to come out and like look at the electrical or something one of the days that it's going in, like he can do that. He doesn't need to sit there all day, every day, because there's going to be a building there at the end of the day that you can go look at. This is all work that's being accomplished hundreds or thousands of feet below the surface of the earth. And so, yeah, my plugging report might say, look, there are plugs set here, here, here. Here's the composition of the plug. Here's the density of the plug. There's nothing to back that up. There is no proof of work that currently exists. And so I think we're lulling ourselves into a false sense of security that wells have been plugged to a certain standard when we don't have good third-party verification that that is actually true. So I guess my last point here, another sort of actionable thing, is that the P&A process can be improved at a cost. And this is all anecdotal, right? I don't have data to support it for reasons that I've already stated, because there isn't really any study that's been done on this. Most of the regulations are currently calling for either a Class A or a Class G or a Class H neat plug to be set across, the hydrocarbon producing formations and across any casing stubs and shoes, yada yada yada. And that's great because you have to put something on paper, but it's a Class A neat slurry isn't the right application for every plug that you're going to set just because it happens to be in that state. Sometimes 2% calcium chloride might be good to add to that plug, but that's not put into a scope of work for any of these bids. Like it's never developed to that level. And so do you think a contractor is going to willingly spend more on a tailored cement slurry to make a better plug when the base material is all that's being called for? No, that's not going to happen. There are no requirements to test cement. There are no requirements to test the mix water. There are no requirements to let plugs cure to the proper set times that API might recommend. There are not enough requirements to have to tag plugs and verify where they were set. There are no requirements to treat the well bore prior to pumping cement. Many states don't require pulling uncemented casing out of the well to get that rock to rock seal that George brought up earlier. So private operators in many cases might want to do that because they want to get it right the first time, lest they have to go back and do the job again. But I don't see it happening in many orphan well programs for the most part. And so we are following things like cementing practices right now that would never fly if you were drilling a new well, but for whatever reason is fine if you're plugging a well. One point that I skipped here is the idea of cleaning the well bore out. So many orphan wells require clean out operations. You're not just tripping in the hole and setting a cast iron bridge plug and like cementing your way out. In many cases, you are fishing or milling, and I would always lean toward the fishing expedition. In other words, I think that finesse always needs to be favored over brute force, because you get yourself into a lot less trouble. The worst case scenario is you couldn't fish it and you have to go to milling. But once you start drilling on something, more likely than not, you're going to kick off outside that well bore and start drilling new hole, and you create many, many more problems for yourself than if you would have just taken the finesse approach to begin with. The problem, though, again, is finesse requires more upfront money, more upfront cost, in order to potentially save on the larger costs that will happen if the milling operation goes wrong. Um, and so I think that one other thing that I've put here is like ensuring their proper barriers are placed at like casing shoes. The To me, like I said earlier, I think making sure you have competent shoe plugs is actually as equally important, if not more important, than making sure you have a bottom hole plug, especially in a well that's completely dormant, where you have no oil or gas shows, where you have no brine shows. Like, get ensuring a proper seal of that casing seat is really critical. And so again, if it's just because it's not required that, let's say, uncemented production casing is pulled, if you have the ability to get a good plug across an intermediate casing seat by doing that, I think it absolutely should be a requirement, and that should be across the board at a federal level. I see no reason why you can't pull production casing out of a well other than to save money. Lastly, here, I'll say, post-plugging monitoring. If we want to eventually collect data on this, we got to stop cutting wells off 4 feet below grade, welding a steel cap on them, and burying them. There should be above ground candy cane monuments installed on everything that you could go out and test after the fact. And it doesn't probably have to be forever, but it should at least be there for a while so that we can at least start collecting data on what's working and what's not. Because right now it's taking who knows how long to discover that one of those wells that's buried 4 feet underground is actually the plugs have failed and there's something wrong. Usually it's somebody's groundwater's gotten contaminated is when you finally find out that the plugging job wasn't done to a standard. So we absolutely need better standards for post-plugging monitoring. I'll get off my soapbox now. That's all I got for you today, but happy to take any questions.
Thank you, Luke. That was really good.
Yeah.
Can we at this point we are collecting questions from the public audience. We're also, if anyone from the committee is going to take priority in terms of questions. So are there any questions from the committee at this point?
I'd never heard the business referred to as like recreational plugging, you know.
Okay, we've got two. So David and Mileva. So David, you're up first.
Hey, Luke. No, thank you. Excellent presentation. My name's David Parent. I'm with Chevron. Spoke to my heart about cutting and pulling free casing. That's a hot topic too. So, I feel your pain on a lot of that. But what I'm actually interested in is, and you touched on it a little bit, is, and I've seen it on your website for, a client that y'all are doing those real legacy wells with no casing at all. They ripped it out the ground, or they completed that way in the 40s and 30s, and we have quite a few of those. And they're also troubling in places we want to put CCS sites and all. So we're talking about re-entering an old uncased open hole. But it seems like y'all have, I'd like to know more about your solution with using a cable tool rig and the clean out success. Maybe not going all the way to 2,500. And I think that's right. Is we've got to balance, you know, good for the sake of perfect, or however you want to look at it, right? Like, what is the ultimate objective? Protecting fresh water, things like that. But it is, there's a lot of thoughts that it's not even feasible at all once you get out of the casing, and I don't know if that's necessarily right. So I like to understand that practice of P&A for those special type of wells.
Yeah, that's the cable tool cleanout has become very much of an art form now, that not a lot of people are experienced on that anymore. And it is purely for these sorts of situations. You can't circulate in the well bore. It's going straight, into the aquifer if you try to do that. So you basically are resorting to the methods that the early wildcatters used, right? You are sacrificing um, the two barrier like well
Well
control
control.
methodology and you are accepting that risk because there is no other way that you're going to be able to clean that well out. Now, we try to mitigate that as much as possible. We try to be able to take and get cleaned out using cable tools until we get below the aquifer. And when we feel we're comfortably below that water table, we will cement new casing in that well so that we can get circulation. And in many cases, we'll move the cable tool rig off of that job and bring in a rig that can, do a conventional
Yeah.
pump and swivel clean out at that point. But that's the best thing that I could recommend is in those wells. And we run into it a lot, particularly with the wells that have just wooden conductor set at surface, is we've got to be able to clean out, get new casing cemented in below the freshwater vein, and then resort to a more conventional P&A method after that.
And just a follow up to it. So, and obviously that's in Pennsylvania, but have y'all been doing it anywhere else? And what is just a ballpark success rate in doing it in that manner? I know it's all,
We've only used cable tools in Appalachia at this
okay,
time. But I would say the success rate is fairly high.
okay,
It's slow, right? You have to
of
accept
course,
up front that your rate of penetration is not going to be as good as if you had a bit on and some drill
yeah,
collars. But if you can accept that, then I've seen very high success rates with it. I can't quantify it right now, but
right,
yeah.
okay, perfect. I appreciate it. Thank you.
Yeah, thanks for the question.
One. Mileva, go ahead.
Yeah, thank you. Hey, look, fantastic presentation, straight from your heart.
Thanks,
I
Maleva.
really appreciate that. So there are certain things that you mentioned that really tie up nicely with what Dwayne said earlier today on this is a money problem. And unfortunately, I don't know much about money, but for this committee and for the consensus study, if you could like pick a couple of points that we could focus on and basically provide in the final product, which should be this publication at the end of this, that would help companies like yours scale up. Because if I am to summarize all this, the number of P&A jobs is not going down, it's going up. And there are apparently not really many companies. Why would someone even want to do this if there is not really good financial incentive? So I think there is something else, like in case of your family legacy here, you want to do it right because it's the right thing to do. So what could we do to serve this purpose with this study?
That's a great question. I wish I would say that I was in it for the love of the game. I absolutely am in it to make money, and I still am optimistic that someday I will be able to make money doing this, even if it's not today. I think what really needs to be thought of is one of the most damaging metrics that I see out there is what's the average cost of plugging?
Oh, yeah.
And aggregated across big like samples of wells, right? And people get locked in on that number without standard deviation never gets thrown in with that number, right? And like well priority never gets thrown in with that number. So like let's say Oklahoma or Kansas, for example, with their initial grant, just wanted to get the most orphan wells plugged with the money as possible. And so they just found the cheapest 900-foot static oil wells out there and just plugged them all for like $7,500 a piece. it begins to read into the consensus that, okay, well, the average cost of plugging should be $30,000. But if if the biggest impact is being made on those wells that are super emitters or wells that are in, a playground in Pittsburgh, we have to accept that that should probably cost more. We're getting more ROI, return on our investment from an environmental standpoint by spending the right money and making sure that it's done permanently there. And yeah, maybe the old crude lowbrow method should be used on some of the 900-foot shallow oil wells throughout the country. Maybe we don't need to be using thermite plugs on those things. And I think it's just being able to differentiate swimming in a pool versus swimming in the ocean and just not always um, creating false analogies because a well is a well is a well. It's not true at all. And so I don't know if I answered your question there, but I think the way that
Yeah.
it would be more valuable to me is I work a lot on high impact projects and not so much on just the cookie cutter 1,000-foot, easy plugging jobs. But those jobs, the cost data from those jobs influence what states and operators and everyone else are willing to pay on the ones that need the extra attention. And so we really need to get people's knowledge up there that these should be treated as different things.
So this is really not one size fits all. We really
Correct.
have to differentiate and classify a few things to help moving forward with the
Correct.
cost and the planning and the expertise. Thank you. Excellent.
So I'm gonna, Mary, before I go to you, there's a question that came across from the webinar, and I think it has relevance. It says, what policy, financial, or operational changes could be implemented to create a viable economic incentive for operators to engage in well plugging and abandonment while ensuring environmental compliance and long-term integrity? Big question. Sorry, but
It's a big question.
it's a
Yeah.
really big question.
Um, I think I'm an oil and gas guy. I mean, I'm third generation in the oil and gas industry. It's given my family everything, it's put food on our tables for 55 years at this point. But I'm not one that's going to shy away from criticizing the way that extraction has been done in the country for the last 150 years. And just because it's always been done that way doesn't mean it should always be done that way. And I think one of the biggest problems out there is that big company drills a well, produces it until it can't cover its overhead anymore, passes it to a middle-sized company that can still make some life out of it, who then passes it to a smaller company, all the way down until now we have like individuals with maybe 2 employees that own hundreds of wells throughout the country. Nobody did anything wrong in that entire chain of events. Everybody was seeing economic value all the way down, but now society has to pay to clean up the problems where economic value was extracted by the various parties along the way who don't have to clean up the problems. And so I do think there probably needs to be stronger, not necessarily well bonding up front, but I know that there's a lot of like transfer bonding things that are going into a place. So if you have a choice, do you want to bond the well that you're transferring to another party, or do you want to pay to plug it? I think that's probably the economic decision that needs to be implemented if we want the problem not to continue to grow bigger than it already is.
Thank you, Luke. That's a good answer. Mary, one more question. Dwayne, you said you had a 30-second answer to the comment on this question.
Thank you, Missy, for that. The way the regulations have worked has created a moral hazard, and people trying to make a living have gotten in this situation. But I've been looking for years, and I can't find any economic benefit to a company from plugging. There's nothing we can do to make it an economically profitable thing. It's always going to be burying your money in the ground. The only way to get it done is with some sort of external requirement. And the question then becomes who pays that? Is it the public or the industry or no one or do we just allow the leaks?
Thank you, Dwayne. Mary, go ahead.
Thank you for the really nice presentation. And yeah, the whole question about where does the money come from is a good one. But I wanted to ask a slightly different question and highlight one of the things that you said about data. And well, there's a lack of data. I think we can all agree on that. And we need to collect more data, and there's different ways to do it. And what is enough? That's also a big question, and something I asked earlier. But there's another third question about data quality, which is something that you've also alluded to, even like the plugging reports. How reliable are they? And from a monitoring standpoint, I mean, the Alberta surface casing vent flow database is great for well integrity. However, there's researchers have been trying to do all kinds of analysis with that data, and trying to find doing root cause with that has been super challenging, and the results have been essentially inconclusive thus far. I don't want to bring up my lab's work, but one of the things that we did was we went to a bunch of wells and did measurements. And then we didn't check beforehand, but we checked afterwards and compared it with the provincial data. 60% don't match when there should be, they should be on the list. They're not, or, it doesn't match. So, who should be doing the monitoring and how can we do it so that we get reliable data? I think that's a hard question, but I'm going to throw that to you. How do we get good data and who should be doing it?
It is a hard question. I've done a little bit of methane monitoring myself, let's say, and like we go out and measure a well one day, and then you go out a month later and the leak is 50% different than it was a month ago. And then you go out a month later and winter set in and there was some water coming up with the leak. And so the leak point has totally frozen off now, is zero. Like it was a leaking well in the summer, it's not a leaking well in the winter, right? It's a hard question to answer, like how we gather the data on the leaks that are out there, and how we extrapolate that and say, okay, well, what is the actual environmental impact? Because if a leak in July isn't the same as a leak in October, and that's not the same leak that is in February, how do you build a dynamic enough model that can really do that? Who should be responsible for it? I like, at least it's crude, but I like the provisions within the IIJA formula grants that pre and post plugging methane testing and quantification should be done. Um, I don't know how great the data will be because it's not going to be a random sample, right? Like these are all the wells that will be chosen for these projects aren't required to be known emitters. Each state has its own priority matrix that they're allowed to package wells in. And so I don't know that that's going to be super useful. But it's the best way that I think I know how right now to start collecting data in larger quantities is tying it to federally funded well plugging projects.
Thank you.
Are there any other questions from the committee? Oh, Jeff, go ahead.
Hey, Luke, good presentation there. And Jeff with Slumberjay, so in the fellow service side of things, we do plug hundreds of wells a month. We work with no regulatory state body, and we don't do anything that you do. And it's for all the reasons why you said about where the financial incentives are. We work on places that have either required a specific style of plugging and ensuring and materials used. This is not going to be your neat cements. This is going to be flexible or self-healing or expansive cements. This is going to be a step above, quite a bit above what is normal, and driven by places like Colorado and the Bakken and in other places. And what has driven better plugging practices is regulations. but still none of which is being put to bear on orphan wells. The regulatory bodies has put in orphan wells in the responsibility of the operator. And that was the success that's happened there, is that they, to continue primary work, they must take care of all known orphan wells in the area, right? That has driven to better practices in orphan wells. I think the challenge when we're talking about orphan well study here is that there is no financial owner, and it's always going to be driven to how can I get as many done with my budget as possible. The likelihood of how can I get as many done as possible for the eternity has been used. Portland cement doesn't last eternity. I've never seen that data. Matter of fact, just look at the rainwater and what it does. So you can probably make your own conclusions about Portland cement and its eternity. But those are the factors. I think that there has to be a compelling event that establishes that there is a certain standard that as a society we choose to uphold when we're talking about wells. Otherwise, I don't see a financial model, Luke, that will just drive the P&As. The financial incentives themselves will drive better plugging practices and better research and better data systems and all these things. So that's one of my comment. With that in place,
I will say one thing that is encouraging to me, and I do believe that carbon credit markets will drive better P&A practices going forward, because there is a financial disincentive for a well that leaks. If you've created a batch of carbon credits saying that you've taken a 12 kilogram per hour leaking well, and you've extrapolated that over 20 years, and then you sold those credits into the free market, and then it comes back later that that well is leaking and those credits are invalidated, and some company reported on their 10K that they were carbon neutral in this year, but they actually weren't carbon neutral because the credits that you sold them were garbage, you're going to be sued very heavily for that. And so there's a lot of incentive to plug wells right if that's sort of your motivation. I'm dipping my toes in those waters right now. Also, I think industry, if they are plugging wells sort of in that area of review from an area where they're trying to do further development, the last thing they want is communication with a nearby orphan well. So they want to be sure that that well isn't just plugged to the bare bones regulatory minimum. They want to make sure that they're plugging that well to ensure that that communication doesn't happen, which is probably why like Schlumberger would be involved in those sorts of programs, because they want to be ensuring that they're using like the best cement slurry for the application when they're plugging those sorts of wells out. So I agree, there is no direct financial incentive in that. It is just burying money at the end of the day. But I think that the ability to repurpose land, the ability to open up areas for further oil and gas extraction, and the carbon credit markets are at least tangentially something that would incentivize people to raise the P&A standards that currently exist.
Do you think that we have, we talked a lot, all the decisions we need to make need to be data driven and also have data to back up our statements, right? And a lot of what the orphan wells and failures is going to be anecdotal because true data is hard to find. I also find that, let's just go to the primary market, which we have a lot more horsepower under. The rate of sustained casing pressure, a lot has been said about Alberta, right, on this meeting today from the morning presenters. That why that is because their method of recording methane leaks and sustained casing pressure they call vent flow, surface vent flow, is just more regulatory required and it's more robust. So thus for we have data. When we go through the states, I would reckon that sustained casing pressure is not widely recorded or widely communicated up holistically. That we know that there's some problems, but the actual numbers are always going to be large.
Yeah, I agree with that. I think 40 to 50% of my revenue right now is doing nothing but surface casing pressure remediation activities. So
So my thing is, if we can't get it right on primaries and we're still seeing vent flows, we probably need to relook at our P&A techniques, right? Because
yeah,
the I don't what I'm saying is I don't know if we even really understand, or abandonment failures, or looking well enough at it. And that data that we're trying to look for is hard to find. And so we say, well, let's just look at time. We know we have failures, so it's probably time as a factor. I have been involved in P&As that have been days before bubbling has happened in the north, especially in your area, Luke, in the neck of the woods in Pennsylvania. I have been there, and I have taken 40 cement jobs to squeeze off sustained casing pressure, which is almost impossible sometimes by the mechanism by which it gets to surface. I just think we as an industry have to understand. I believe that when we talk about methane credits and people starting to look, and you put money to something, they're going to start looking. I think we're going to find that there's a lot more leaking and a lot more. Oh, there's money in methane. Oh, here it is. It's everywhere. Type of thing might happen, and then all of a sudden, you're right. It might kick on to a little bit better attention. Like, oh, that methane has money now. I'm gonna stop it and make that money, and that might be a good strategy. But you deal with all this all day, every day. Is there real? What's the best way to say it? There's real traction on people actually going after how well that are we actually getting? Is there a bubbling methane? Are we really looking 50% of the time even to really know if it's there? Are we just capping it and burying it and saying it's not a problem?
absolutely just plugging it and burying it. Like there are no interested parties, like I've said before, in knowing whether we did a good job or not. Unless, like I said, with a private operator, if they know they're going to get inspected post plugging, there's one well we've been on for the same customer 5 years in a row. We just go back and drill the cement out and replug it every year. They said at this point it would have been cheaper. It was a stranded gas well. It would have been cheaper for them to lay an individual pipeline to that well and hook it up than what they've spent plugging it and replugging that well. So yeah, no, it's
that just goes to the committee as we look for data. I mean, I think we have to look at all this data through lenses, with glasses on, and understand that the data we're getting is after all this headwinds of trying to get data. That this is what we're up against, is that orphan wells are immediately put underground and nobody's usually looking. And so when we say, well, what is the failure mechanisms of orphan wells, which might be different than main, operator owned, because operators owns incentives might be different than what the orphan well regulations have been. And that may be something for us to tackle, is around the data part of this. Is where we're going to struggle the most, is one of my things, is just real 100% data that's driven. And that's why I think Dwayne, the previous presenter, pointed to data as being one of the best things we could do. And if we can
just the last thing that I would say on that is orphan wells in large part are plugged in the crudest, most lowbrow, cheapest ways possible. And I'm not saying that's wrong. I don't want to say that shouldn't be done on those little 900-foot oil wells that are out there that you can plug for $5,000 each. I think that there's a time and place for that. I think you've just got to know where lowest bid, lowest, cheapest price shouldn't be the method employed as to who and how you choose to plug more high priority orphan wells.
Should be driven on what we're trying to do and what the lithology is telling us and what is stratified. Like salt flows are a huge problem in certain areas, not in others, right? And you understand that. And the corrosive nature of fluids has changed, as well as that 10 years ago, you would not see them corrode on intermediate casings, and now they're corroding within 6 months. Nothing's changed in the well design. In fact, the cement and the casing design is more robust today, and they're filling sooner. What the industry is doing is very, very different in the Permian than what we used to do. And so I think that should drive the cost and the thing. Cement in whole is better than cement not. So we should be going after those 900 foot. We should be cementing stuff. It's just we've got to really focus on that last part, is like how well they're doing, because data-driven analysis is going to be a big challenge, and we're going to have to make some assumptions off of what we have, but we need to put it through some filters and understand what data that we're getting. And Alberta, it does have more data. In Canada does have some more data than we do. I like the fact that people are looking there to possibly get some more input. But that's it, Missy, for me. Thank you.
Well, thanks, Jeff. Jim Bolander.
Yes, it was interesting the back and forth between Luke and Jeff. I think there were, obviously some common themes that y'all touched on back and forth in that, amongst that, from the regulatory, perspective is that, in many states, plugging regulations, there's not a common link, especially on cement standards, qualifications and such between primary cementing and plugging cement. I think, there needs to be looked at that in terms of that. I do know Colorado is a state that requires their plugging cement meet the same standards as their primary cement. In addition to that, when they revised their regulations, they also required additional zones to be isolated during primary cementing, which from a prior analysis caused a lot of sustained casing pressure in certain areas within Colorado. When they made those regulation changes, they also required statewide braiding head testing to monitor for sustained casing pressure. So we at least have, at least for Colorado, statewide data, for the last 5 years, in addition to regional data prior to that. Other states who are monitoring sustained casing pressure are New Mexico, but it's very regional. And Pennsylvania has started it, especially with their monitoring of surface casing vent flow, primarily around most of the coal production. So there's that, but really what I thought was that kind of the disconnect of what we require operators or regulations to look like for plugging a well that don't quite match up with the construction of a well. Just kind of wanted to highlight that.
Yeah, and so the one thing I would want to ask Jim, I've never plugged an orphan well in Colorado, but my sense is that, is there any way to prove that the cement or the cementing methods that were used in the plugging job on that orphan well actually do meet the same standards that are meant on a new well construction? So is there a data acquisition report from the cement job that's stapled to the plugging affidavit that I could pull up and read, like, okay, here is the density of the cement slurry, the pressure, and the rate at 10:02 a.m. on May 15th of 2024 was happening on this well? Or again, is it just something that the plugging contractor just signs off on and says, yep, it was good, and a green oil and gas inspector countersigns that same affidavit, and then that's proof that the regulation was followed? What I'm saying is that there's a lot of times that regulations and best practices deviate substantially from what actually happens in the field because of enforcement issues.
Right, I understand that, but I would ask Jeff, who talked about having plugged more difficult wells in Colorado. What do they require in terms of well data submittal for post plugging? I do know that there are requirements for testing cement, mixed water, free water requirements. So they moved that from primary to plugging, but what's actually required, do you submit your cementing records, or is it just as simple as filling out the form? That part, I don't have haven't reviewed that kind of data yet.
So I'm not submitting to states directly, right? I'm working for the operators. So the operators that we work for in Colorado, we do submit real-time data acquisition and lab testing on every well, right? Every well gets lab tested. I will even make a comment. The wells, the slurries that we're using and the practice that we're using in Colorado specifically are usually like the slurries are better performing slurries than what you will typically see in other primary workspaces in certain of the areas.
Expect that out of SLB. What I would say though is that
Even what we're doing in SLB,
the majority of orphan wells, I would guess, in Colorado are not being cemented by Schlumberger.
The majority
and so-
not. I would suppose it depends. What I see in Colorado did, and this is also why the rig count in Colorado is probably not as high as it could be, but I think it was the right decision. Is that they have put the ownership on, if you want to drill here, you're going to have to take care of the wells that are already existing in your acreage.
Right.
And I don't know that I think it's an approach that is working, as far as people taking ownership and saying, I am actively going to solve this problem so I can actively have a drilling campaign.
Yeah. That would be tough in Pennsylvania because you'd inherit like 20,000 wells for every
you just
couple
would
square
see,
miles of
you would just
acreage
see
you might
people just go, well, it's not my acreage. I'm out. And or but even Pennsylvania has done some good things with surface vent flow, saying you're not going to get new permits until you can prove that you can cement a well that doesn't have sustained casing pressure.
Yeah.
As an example. But it all goes back to data, and the post job data, I think, is critical. How we monitor, how we continue to monitor after a job, that is where I think the secret sauce is, and will drive regulation and drive knowledge is the data.
All right, let's move on. Mary's been very patient waiting. So Mary, go ahead.
Oh, no problems. Yeah, it's my second question, so I could wait, but so yeah, thank you for that, and thanks everyone for the discussion. So this is more kind of like a recapping, at least for me, but there is also kind of a question embedded in there. So there are kind of a couple words that have been used a bit interchangeably, not just today, throughout today, and to me they're leaks and failures. And so, how would you define those two? Because a failure could be, okay, not meeting regulatory requirements, or failure could be some kind of a leak, but then, what is that leak? Is it methane emissions observed at the surface? And what is that detection limit? What is the lower limit below? Because you're never going to get zero. If you can always find more sensitive measurements to give you values, smaller values, if you can spend the money. Right. And so then there's also the subsurface component, are there leaks happening underground? And of course, there's costs associated with it, and a range of different methodologies. So, but I also like what you said about, what's acceptable heat in one location it's not the same as what's acceptable in another location. So if you're at a well next to a school, you want to probably have a higher standard, and you really don't want any kind of leaks whatsoever. But maybe somewhere else, you're okay with some leaks. But just wanted to ask you about your definition of leaks and failure and how interchangeable they are.
Yeah, I mean, I suppose at any level a leak is a failure, right? Because the whole reason you cemented the casing in the well, or you put steel casing in a well, or you plugged a well, was to stop the flow of fluids to surface or into groundwater. And so any presence of those hydrocarbons or brine at surface or in groundwater is a failure. I just think it's impractical to say that we can ever stop all the leaks everywhere. Like, we don't have the resources or the political will to do anything close to that. So it really comes down to prioritization and sort of asking ourselves as a society, whether that's the United States or Canada, as to where do we get the most bang for our buck? Where do we need to get it right? Where do we need 0 parts per million, 0 grams per hour methane at surface? And where is 12 grams an hour at surface acceptable? Where do we need to be sure that there is 0 chance that anything ever gets into this stream? And like my business is in Bradford, Pennsylvania. The water table there is so polluted at this point from 100 years of basically unregulated drilling that if a little bit more gets in there, it's not going to do anything to it. I mean, you can't drink the water pretty much. So I guess what I would say is you just gotta, I hate to be so like subjective about this because we want to come up with more general principles for everything. But the general principle should be is to not treat all wells as the same priority and understand like what we value and where the money should be and the resources should be spent.
Thanks, Mary. Thanks, Luke. Mileva?
Um, okay, so we talked a lot about what doesn't work and the problems. So I want to try and maybe shift a little bit towards the positive. You have done so many of these orphan well P&As in Pennsylvania and elsewhere. And there are a lot of focus here on the surface leakage. I'm kind of wondering what is missing or what works based on your experience for the subsurface. I'm kind of now moving towards the contamination of the water that you just mentioned is already past the point of in your area, but maybe we can do something not to have that experience elsewhere.
The thing that I advocate for the most is pulling uncemented production casing, particularly in areas where the top of the cement is below the intermediate shoe. It's not a requirement in a lot of states. All you need to do is perforate that casing and squeeze. It's the simplest rule that should be enforced everywhere is that if you have uncemented production casing that is below an intermediate or surface shoe, it needs to be cut, it needs to be pulled, and you need to have a wall-to-wall barrier put in there. And that plug is, in my opinion, the most important plug that you're going to place in that well. And so that is the one that we should be prioritizing above everything else. And so if there's anything, I know I just poo-pooed on the whole industry and why it's terrible to be in it all day today. But if there's one thing you could take away is that we need to be putting intermediate and surface shoe plugs in a scenario where there is as little steel as possible in that annulus.
Thank you, Luke.
Yeah.
So at this point, I don't have any other questions. No one has their hand raised from the committee. I don't see any online. Oh, there we go. Jim, go for it.
Hang on, I'm just getting my mute off. Hey, I just want to follow up on that because I'm kind of curious on what existing in your experience on because I get why we want to pull that long string, and I know there's probably sometimes there's challenges with the borehole sloughing in and all that kind of stuff, but you know, like what's in the current practices, how is it more frequent to leave the casing or more frequent to pull? Is this, I mean, there must be some people that are pulling casing. It used to be you pulled casing to reuse it.
Yeah, that's a great question. So in like Pennsylvania, Ohio, New York, and West Virginia, it's required you pull free pipe regardless. I think that's not a great idea. In some cases, we've had to pull surface casing because it was uncemented because the regulator interpreted it as free pipe.
Yeah.
And like we're doing way more harm than if we just left that in the well.
Right.
But even if we're just thinking about production pipe itself, if you're cemented up into the intermediate casing 500 feet, what is cutting and pulling an
No, I know.
additional
I'm kind of curious. What is the practice? More than likely, it's left, or is it?
I would say on average, more than likely, it's left when pipe prices are low.
Okay.
So,
Okay.
where the salvage value isn't great, it's expensive to get casing jacks and wear line and all of that out there, and it adds days to the rig. On a deep string of 5.5, if you're recovering like 6 or 7 thousand feet of 5.5, you could add $20,000 or $30,000 of expense to that well
Okay.
by the time you do all of the additional steps. So in those scenarios, it would absolutely benefit an operator to just perf and squeeze their way out.
Okay, so it's 20 or 30,000 in the value of the casing in that case, a
Depends.
variable, but
Yeah, it depends on the pipe market at that time. Sometimes
you're
it can
not,
justify pulling it. Yeah.
yeah.
Yeah, let me follow on with that. We occasionally have a very negative value on pipe market when you have norms for pipe. Your thoughts? I mean, do you get much on casing, or is it mainly the tubulars and other hardware? Or maybe you don't see a lot of norms in your neck of the woods, but there are places I've worked where any solid that came out of there was glowing in the dark. And so, that none of that stuff is valuable for us to take out. We'd much rather get rid of it. We'd much rather bury it
Right.
right there. So, your thoughts on that? Suggestions?
Again, I think that regardless of the economics, if you are choosing to perforate and squeeze cement behind production casing as an intermediate shoe plug or a surface shoe plug, that is the wrong way to go. I think that regardless of the cost, it should be cut and a solid wall-to-wall plug should be put in there. But agreed, 100%. It is rare that in my experience that the salvage value of the pipe pays for the cost of extracting the pipe.
Sure. Well, you're not going to be able to circulate successfully on really old wells because the dirt, you can't move the pipe, you can't rotate, there's solidified mud back there that have got channels that are inaccessible to injected cement and fluid. So you're absolutely right. We're not going to be able to successfully circulate behind pipe. But I've just,
but I've seen my fair share of operator that will give one attempt, and we'll see the stringer up the hole on the bond log. People say, you can't see, dehydrated mud or whatever on a bond log. I think, okay, sure, but we can still do a stretch test. We know where it's at, where the free point is at. And generally what's happening is operators are saying, well, we tried once, we're going to perf and squeeze our way out now, rather than really putting the effort in.
And I have one other, comment or question. This morning, Dwayne showed us this, thing where the number of orphaned wells, albeit a large number, is small compared to the number of, future orphans potentially, or the a long time idle wellbores.
Yeah.
Presumably, some of these wells this next batch, I mean, they have wellheads, they have, locations. They should be simpler. Am I living in a fantasy world there, or?
No, you're right. It's just how long does it take those to hit the orphan list? So if they're idled for 20 years before they're declared orphaned and eligible for the money,
they probably are already orphaned. I did a little checking.
Yeah.
I drilled some wells in a water flood in Oklahoma as a summer intern in 1975. And I remember one of the wells, our map got revised after this well. We didn't have any sand to inject into, but somebody thought they did, and they cemented the well. Nobody bothered to plug it. It's never been perforated. It's still there. It's an idle well. That was 1975. So that's an easy one to plug potentially, but it's never going to be plugged until someone makes it a decision.
Yeah. Someone in a Capitol building somewhere has to make the clicking motion to move it from idle to orphan well status before we can do anything about it. And my fear is that a lot of these, because states are hesitant to add more wells to their orphan well inventory, and we can kick it down the road to the next guy, maybe he'll add it to his list, that these will sit in idle status for a very long time until we start to have integrity issues and the access becomes harder and the costs continue to go up.
Thank you, Luke. I think we've beaten on you enough. We really appreciate all your discussion and the answers and everything. So we're going to let you go and let you get some rest and a cup of coffee. And thank you very much. It was very informative. Noelle, I'm going to turn it over to you for logistics as we go forward.
All right, great. Thank you, Missy. Thank you, Luke, so much for this afternoon session. So we'll go ahead and close a little bit early. Thank you also to everyone in the audience and our other committee members, staff, panelists for tomorrow and from earlier today for sticking on as well. It's been really great to have you all present for the discussion portions.